Welcome back. Today we're going to talk about balanced search trees, which will lead us to an ultimate symbol table implementation that can provide fast performance for all the symbol table operations we've looked at, guaranteed. So here's a review of where we were with symbol tables. We took a look at last time at the binary search tree, which if things are well modeled by random insertions, have great performance. They get search and insert done in time proportional to log base 2 of n, and they support ordered operations. But really, our goal is to have these operations be guaranteed to take time proportional to log n, because we don't have control over the order of operations, and they may not be random at all. And in fact, in many real applications, they're not very random. So that's what we're going to look at now, is try to find an implementation that can guarantee to be fast for all the symbol table operations. That's our challenge. So what we're going to talk about to do it is an algorithm that actually a pretty old algorithm called 2-3 trees in a particular implementation that requires very little code called left-leaning red-black BSTs. And then we'll talk about a generalization called B trees. And these methods are all widely used throughout our computational infrastructure. To start, we'll talk about 2-3 search trees, which is a model that underlies the concise and efficient implementation that we're going to look at. So a 2-3 tree is a way to generalize BSTs to provide the flexibility that we need to guarantee fast performance. And the idea is very simple. We allow 1 or 2 keys per node. That is, we allow for the possibility of something called a 3 node that can hold 2 keys, but then it has to have 3 children. In a regular BST node, a 2 node, we have 1 link for the keys that are less than the key in the node, and 1 link for the keys that are greater. In a 3 node, we need 3 links, 1 for less, 1 for between, and 1 for greater. Another property of these 2-3 trees is that we're going to have perfect balance. That is, every path from the root to a null link is going to have the same length in a 2-3 tree. So as I mentioned, the symmetric order is part of the definition of a 2-3 tree. Every 3 node has 3 links and 2 keys. The left link is for the keys that points to a 2-3 tree with the keys that are smaller than the smaller of the 2 keys in the 3 node. The middle link points to a 2-3 tree that contains all the keys that are between the 2 keys. And the right link points to a 2-3 tree containing all the keys that are larger than the larger of the 2 keys in the 3 node. Okay, let's take a look at a demo of searching in a 2-3 tree. So say we have this 2-3 tree here, and we want to search for whether or not H is one of the keys in the tree. So we start at the root, compare the search key against the key or keys in the node, and follow the link corresponding to the interval that we know must contain the search key by the definition of the tree. And then we recursively continue the search. So if we're looking for H, it's less than M, so the only place it could be in this 2-3 tree is in the 2-3 tree on the left link, so we follow the left link. Now we compare H with E and J, and in this case it's between, so now we're going to take the middle link. That's the only place that H possibly could be. And in this case, that node, one node 2-3 tree contains H, so that's a search hit. Let's take another example for unsuccessful search, a key that's not in the tree. As usual, we start at the root. It's less, so we go left. It's less than both keys, so if it's in the tree, it would have to be on the left link. And it's between those 2 keys, so if it's in the tree, it would have to be on the middle link. And that link is null, so that's a search miss. So the search is a natural generalization of the search in binary search trees. Now what about inserting? Well, it's a similar type of strategy as with regular binary search trees, except that we manipulate the 2 and 3 nodes to keep perfect balance in the tree. So the easy case is if the key winds up in a 2 node at the bottom, like this one. Suppose we're inserting K. K is less than M, so we go left. K is greater than both keys, so we go right. K is less than L, so the search ends at the left link of L. And to perform an insertion, all we need to do is replace that 2 node with the 3 node containing K. Now K is inserted into the 2-3 tree and it satisfies all the rules. Now if we're inserting into a 3 node at the bottom, we have to do more work. And specifically, the work we do is we add the key to a 3 node to create a temporary 4 node and then split up that 4 node and move its middle key into the parent. So let's see an example. If we're going to insert Z into this tree, it's greater than M, so we go to the right. It's greater than R, so we go to the right. Now it's greater than X, and that's a null link to the right of X, so the search ends there, and what we'd want to do is insert Z into that 3 node. And the way we do it is first make a temporary 4 node that replaces that 3 node. And then that's not a 2-3 tree because it's got that one 4 node with 3 keys and 4 links. But what we can do is split that 4 node and pass the middle key up to its parent. So split it into 2 nodes and pass the middle key to the parent. That's kind of a magical operation, and believe me, it's easier to get it done in the implementation than the graphics. But now you can see that that local transformation on the 2-3 tree completes the insertion. Now, if that parent were a 3 node, it would become a temporary 4 node and would continue the process moving up the tree. That's a demo of search and insertion in a 2-3 tree. So let's look at a double split like that. So say we're inserting L into this tree. So it goes down to the middle and winds up needing to be inserted in the 3 node in the middle. So we're going to convert that into a 4 node. Now L's the middle key of that one, so we're going to split that 4 node into 2 nodes and move L to the parent. The 4 node had 4 links, and the 2 nodes have 4 links, so nothing has to be changed below. And then this insertion into the parent changed it from a 3 node into a 4 node, essentially adding a link because of the split with the 2 nodes where there was only one 3 node before. But now that's not a 2-3 tree, so we have to split again. And in this case, there's no parent, so we create a new one, and the height of the tree increases by 1. That's the only time the height of a 2-3 tree changes. When the root splits, the height increases by 1. So that's a demo of insertion into a 3 node at the bottom in a 2-3 tree that percolates all the way to the top. Now let's look at constructing a 2-3 tree from an initially empty tree. So if we start by just inserting a key, well, that just creates a 2 node containing that key. And that's a legal 2-3 tree, so we're fine. Now inserting E into that, well, it's going to be, if it's in the tree left of S, that's a null link, so we need to convert that 2 node into a 3 node. Okay, and that's the legal 2-3 tree, so we stop. Inserting A into that, we convert that 3 node into a temporary 4 node, but then we need to split that 4 node, moving E to the parent, and that creates a new root node and increases the size of the tree by 1, but now that's a legal 2-3 tree, so we stop. Insert R into that, it goes to the right of E, convert into a 3 node. Now insert C into that, goes to the left of E, has to be joined with A into a new 3 node. Again, that's a legal 2-3 tree, and we stop. Now we insert H, that goes to the right of E, that 3 node gets converted into a 4 node. That's a temporary 4 node, we split and move R to the parent. Now that parent's a legal 3 node, and there's nothing more to be done. We have a legal 2-3 tree. Insert X, it's bigger than R, goes to the right. There's a 2 node, there's room for the X. Insert P That goes between E and R, the 2-node containing H. Right link is null, so we convert that 2-node into a 3-node. And now we have a legal 2-3 tree. Now you can see this next insertion is going to cause some splitting, wherever it is. So insert L, that's between E and R, so it goes in the 3-node containing H and P. We convert that into a temporary 4-node, split that 4-node, moving L to the parent. Now that parent's a 4-node, and that has to be split, and we create a new root node, and then the height of the tree grows by 1. And that's a legal 2-3 tree, so we stop. So those local transformations, converting a 2-node to a 3-node, or converting a 3 to a 4, and then splitting and passing a node up, those are the only operations we need to consider to get balance in our search trees. All right, so as I've mentioned, and this diagram shows, the splitting a 4-node in a 2-3 tree is a local transformation. It only involves changing a constant number of links. So in this example shows the general situation when the 4-node to be split is the middle link, but the same is true if it's a left or right. And those 6 subtrees drawn could be huge. They could contain millions of keys. But it doesn't matter what they contain. We don't touch them at all, nor do we touch anything above this node in the tree until a split happens. So the transformation that splits that BCD node and inserts the C into the 3-node at the root just involves making that 3-node into a temporary 4-node and making that 4-node into 2 2-nodes and adjusting the links appropriately. Just a constant number of operations, and that's why this operation is in general efficient. So let's look at just the global properties that these manipulations preserve. The 2 things that are critical is that in a 2-3 tree, we always have symmetric order. That is the order that we defined for 2 nodes and 3 nodes. And we also have perfect balance. The distance from the root to the bottom is always the same. And to prove that, we just need to show that each transformation maintains symmetric order and perfect balance. And these are all the possible transformations that we could do. If we split the root, then that's what happens at the root. And if there was perfect balance before, there's perfect balance after with the height 1 bigger. If the parent was a 2-node, then the transformation is a local transformation. And if you look at where the links are, then it's easy to see by induction that if there was perfect balance before, there's perfect balance afterward, because we didn't change anything about the perfect balance in any of those subtrees. And that's true in every case. If the 3 nodes at the right, then this one is 1 higher and those 4 are 1 lower, and afterwards it's the same. If there was perfect balance before, there's perfect balance afterwards, because we didn't change the height of any nodes. We just moved things around locally within nodes. And this is when the parent is a 3-node, then there's the 3 cases. If we split at the left, split at the middle, and split at the right. And again, changing the 4-node to 2 nodes and adding links. If there was perfect balance before, there's perfect balance after, because we didn't change the heights of anything else in the tree. So our operations maintain symmetric order and perfect balance in a 2-3 tree. So that's going to give us a very easy way to describe the performance. All our operations have cost that's proportional to the path length from the height to the bottom, and every path from the root to a null link has the same length. How long can those paths be? Well, it's not hard to see that in the worst case, if they're all 2 nodes, that's the longest they could be. It's log base 2 of n. And if they're all 3 nodes, it would be log base 3 of n, which is less. It's about 0.63 log base 2 of n. So all the paths in a 2-3 tree with n nodes have to have length between those 2 bounds. And those are pretty small numbers. For 1 million nodes, that's between 12 and 20. And if it's 1 billion nodes, that's between 18 and 30. Those are remarkably small numbers. So we're going to have guaranteed performance. Even for huge databases, we're going to be able to guarantee that we can get search and insert done with just 18 to 30 operations. That's quite remarkable, really. So here's what our table will look like when we finish the implementation of 2-3 trees. Every operation is guaranteed to be a constant times log n. Now the constant depends on the implementation, exactly what kind of manipulations we need to do to convert 3 nodes to 4 nodes and so forth. But it's easy to see from the demos and the diagrams that those are going to be constant. Guaranteed logarithmic performance for all operations, which is certainly what we want in a symbol table implementation. Now, what about the implementation? Well, we're actually not going to talk about a direct implementation of 2-3 trees because it's kind of complicated. It's cumbersome to maintain multiple node types. You might need multiple compares to move down the tree. If there's a 3 node, it takes more compares than a 2 node, so it's complicated to analyze. We have to keep track of links as we go up and down the tree to handle the splitting, and there's a lot of cases. I drew all the cases, and there's whether you're splitting into the middle of a 4 node or the right of a 2 node, there's just a lot of cases. So you could do it, but we're not going to because there's a much easier way. So that's 2-3 trees, a model for implementing balanced trees and guaranteed logarithmic time. Okay, we're going to finish up by talking about some practical applications of red-black trees, and in particular B trees, which are a general version. So the idea behind B trees is that often the data that we're trying to store is really huge. There's a large amount of data, and we're going to look at a more general model for external storage, where we work with contiguous blocks of data that are big, maybe 4K or bigger, or maybe even a whole file. And all we want to count is the first time we access a page, because the main cost is trying to find where the page is. Once it's read in, we get to read all the page for free, pretty much. So the real property of external storage, that not your local memory, is that the time required to get to a page is way larger than the time to access data within a page. So what we want to do is try to access data that's out externally using a minimum number of probes. That's a model of a file system that is pretty workable, and so B trees are a generalization of balanced trees that allow for this. The idea is to allow not just 2 or 3 keys per node, but a large number, like the number that can fit in a page. So might be m equals 1,000, m equals 4,000. And well, we've got to have at least 2 keys at the root. And the only other restriction is that we don't want the nodes to get too empty. So we can have less than m, but we want to have at least m over 2. And as you'll see, this is a generalization of 2-3 trees that allows us to build balanced trees that are very, very shallow. Typically, these are set up so that all the data is in the external nodes. And so the external nodes have no links, they just have keys. And they're kept in sorted order. So for example, this is this is m equals 6, this is an external 5 node. So it's got 5 keys, it's got room for one more temporary one. And then what'll happen is when you insert into a full node, it'll split in the same as before, and then we'll pass the split up, causing a split up higher. So the red keys in the internal nodes are copies of keys down below that direct the search. And it's that's a little extra detail that just makes the implementation a little bit easier, and that's the way that it's usually done. But for now, the main idea is that it's like a 2-3 tree, except that we allow way more keys per node. And then when a node gets filled, it splits into two, so a node's always between half full and full. So M is 1,000, it splits in two, and then each side has 500. And then we can use that property of the trees in the analysis to show that it's not going to be very many probes to get to any key. So the search is just the same as we've been doing, just generalized. There's a list of keys at every internal node, and that key tells you that then links for every key that give you a place where your key would have to be. This link is for all the keys in the B tree that are between this key and the next one. And in every case it's that way. So if we're looking for E in this B tree, we'd go down the left link, and then it would go down the second link because E is between D and H, and that's just the way it organized. And then when you get to an external node, you just look for it. That's all searches terminate at an external node, and otherwise it's just a generalization of what we just did. And insertion works the same way. We get to the bottom and then we split. So let's look at just inserting A into this B tree. It comes into the node on the left, and then that makes that temporarily over full. It's got one too many, so we split it into two nodes, and that causes us to add a new entry into this internal node. In this case, it's a C, which is the smallest one in this new page, and that has to be added. And we can move all those over. There's plenty of time by the memory model. We're only counting the number of times we access the pages, and we get to move things around for free. And you could have some hybrid structure where you use something different for the internal model, but usually it's fine just to do that. Now that one becomes over full, so it has to split, and we have to create a new route, just in the same way as we've been doing. So without seeing all the details, you can understand that the same basic idea is going to work in this this situation where we're dealing with much more memory. And so the end result is that a search or an insertion in a B tree of order M, that's where we're putting M keys per page, requires between log base M minus 1n and log base M over 2n probes. And that's going to be a really small number. So say M is 1,000, log base M over 2 is this log base 500. So what power do you have to raise 500 to get bigger than n? In practice, that's going to be like 4 or 5. And we can keep the root page in memory, so that it means for any conceivable application, you can get to any piece of data, even if it's trillions of pieces of data. It's huge file. You can get to any one with only 5 or 6 probes. That's quite amazing. It's really an astounding example of algorithmic technology doing something that you wouldn't really necessarily think that you could do so easily. Maintain a dynamic search symbol table with trillions of keys so that you can get to any key just by looking 5 or 6 places. But that's what B trees provide for us. This is a simulation that shows a growing B tree. So when a page, at the top, there's just one page that fills up. When it fills up, it's red, and that splits into 2 half pages. And then keys get added on one side or the other. So each line in this table, some page is getting a new key, and eventually one of them fills up and splits. And now we have 3 pages, and we keep going. Eventually one of them fills up and splits. Now we have 4 pages, and now this time the first one fills up and splits, and so forth. So the black is the occupied part of the page, the white's the unoccupied part. and full page about the split, then right below there's 2 pages. So this shows the process of building a large B tree. And you can see the amount of black. It's kind of half empty. It's a little more than half empty usually, analysis shows. And people have variants of these algorithms that keep it much more than half empty if that kind of space is a consideration. So as I've mentioned, red-black trees and B trees are widely used as system symbol tables. The Java implementation of tree map and tree set is red-black trees. C++ standard template library uses red-black trees. And it's also used in the Linux kernel and in many other systems. B trees, there's many different variants that give different characteristics of space usage and other characteristics in most databases nowadays that you might use. SQL or Oracle's database and others are based on some variant of B trees because they're so effective. But you really know that your data structure algorithm is used by a lot of people when it appears in the popular culture. My friend Philippe Flageolet, who recently died, but was a famous French mathematician, sent me an email late one night. He was quite excited because he was watching a rerun of an English actually Canadian TV show on French TV. I didn't know he spent his time doing that, but he was very excited because he saw this clip.
It was the red door again.
I thought the red door was the storage container.
But it wasn't red anymore, it was black.
So red turning to black means what?
Budget deficits, red ink, black ink.
It could be from a binary search tree. A red-black tree tracks every simple path from a node to a descendant leaf. It has the same number of black nodes.
Does that help you with the ladies?
Not only is there some excitement in that dialogue, but it's also technically correct, which you don't often find with math and popular culture or computer science. A red-black tree tracks every simple path from a node to a descendant leaf with the same number of black nodes. They got that right. And that's also true of B trees, and both of these methods are very effective and widely used. Now we'll look at red-black BSTs, which is a simple data structure that allows us to implement 2-3 trees with very little extra code beyond the basic binary search tree code. So this is, and actually the version that we're looking at is called left-leaning red-black BSTs. On a personal note, I wrote a research paper on this topic in 1979 with Leo Gibas, and we thought we pretty well understood these data structures at that time. And people around the world use them in implementing various different systems. But just a few years ago, for this course, I found a much simpler implementation of red-black trees. And this is just a case study showing that there are simple algorithms still out there waiting to be discovered. And this is one of them that we're going to talk about. So the idea is that we are going to represent every 2-3 tree as a binary search tree. And in order to get that done, we just need a simple representation for 3 nodes. So what we're going to do is use internal left-leaning links to glue the 3 nodes together. So the larger of the 2 nodes in the 3 node will always be the root of a little binary search tree of size 2 for the 3 node. And the link between the 2 nodes, the left link that links the larger key to the smaller one, we'll color red, and that's to distinguish those links from the other links in the binary tree so that we can tell when we're inserting things which nodes belong to 3 nodes and which ones don't. And you can see from this transformation that it's easy to perform this, see this correspondence. The middle link between A and B, those are the keys that are less than B and larger than A. So that takes 2 comparisons to get to them. The ones that are less than A, less than B, less than A, that's two comparisons for that. And the ones that are greater than B are the right link of B. So just following those three cases, see that this correspondence is going to work. So any 2-3 tree corresponds to a left-leaning red-black BST in this way. Just take the three nodes and split them into little binary search trees of size 2 held together by a red link. And correspondingly, given a red-black BST, then you can get the 2-3 tree if you wanted it. But just look at the properties of, looking at the properties of a left-leaning red-black BST, with reference to what we know about 2-3 trees. First of all, no node has two red links connected to it, because the only red links are internal to three nodes, and those have to have external links or tree links connecting them to some other node. Every path from the root down to a null link has the same number of black links. That just follows directly from the corresponding property for 2-3 trees. A left-leaning red-black BST has perfect black balance. And all the red links lean left. So given a BST with some of the links colored red that has those properties, that's going to correspond to a 2-3 tree. And that's a key property, is this one-to-one correspondence between 2-3 trees and left-leaning red-black trees. Given a 2-3 tree, we saw how to do it. Given a red-black tree, we just make the red links horizontal and merge the nodes together to be three nodes. So all of the operations that we're going to look at for red-black trees can be understood in terms of the corresponding operations on 2-3 trees. Now, the first and really one of the most critical observations is that search in a red-black BST is exactly the same as for an elementary BST. We just ignore the color. Now, it's going to be much faster because of better balance in the tree, but in terms of the code, we don't have to change the code at all. Our regular search code doesn't examine the color of a link, and so we can just use it exactly as is. And in fact, most of the other operations that we implemented on BSTs are also identical. They don't need the colors, but they can all benefit from the fact that the trees are much better balanced. So this aspect of red-black BSTs is an extremely nice one, because the operations that we implemented for regular BSTs involve some complicated code for floor and ceiling and rank and so forth, and we don't have to change that code at all. We just, during the insertion, make sure that we maintain the properties, the balance properties, and by doing that, we wind up with balanced trees, and we make all the operations quick, and we don't have to re-implement, we don't have to change them at all. So first, before we get to the code for insertion, we have to look at the representation. We didn't actually have explicit representation of links. Our links in trees are just references to nodes. You could implement this by building explicit links, but an easier thing to do is to notice that every node is referenced by just one link in a tree, the one from its parents. So you can put the color of a link in the node that it references. So in this case, we have a red link connecting E and C. What we do is put a color bit in each in the node class, and then if the link coming into a node is red, we set that to true. So this simple thing just tests, is a node red? We consider all null nodes to be black, null links to be black. We don't have red links dangling off. That'd be incomplete three nodes. Otherwise, if the color is red, we return true. Otherwise, return false to test whether a node's red. So in this tree, the color of h.left is red, the color of h.right is black, and so forth. So that's the way we represent colors, by putting a color bit in the node for the color of the link that points to it. All right, so now there's a couple of elementary operations that we have to perform on red-black trees called rotations. And the idea is that during the construction of a tree, or during an insertion operation, sometimes we wind up with red links that are leaning in the wrong direction. So we'll need what's called a left rotation. And the job of that operation is to take a right-leaning red link that is there for whatever reason and reorient it to lean to the left. So in this case, we have the right link of E points to S, and S is red, so that's a right-leaning red link. And so that's the before, and what we want to do is reorient things so that it leans to the left. And again, that has to be a local operation that only changes a few links. And just from the diagram, it's not difficult to see that this little bit of code will do the job. If we start with a right-leaning red link, so first thing we do is take the reference of h.right and save that in X. So that's the node that's going to be the new root of the three nodes, so to speak. And then x.left after the rotation is going to be H. And also whatever color H was, well, it looks like it should be black, but actually there's situations where it could be red. Then X is going to have that color because the link coming into H is going to be the link coming into X. And then H's color is going to be black afterwards. And then we return X to link further up the tree, which happens during our standard recursive insert. So that's a rotate left operation. Now the property of this operation that's very important is it maintains a symmetric order. The keys between E and S are still there. We just change the way we get to them, and the keys less than E and so forth. And also we maintain perfect black balance because we didn't change the black height of anything by doing this transformation. All those subtrees, those three subtrees are exactly the same relative to the top and bottom of the tree as they were before the rotation. Now, paradoxically, and you'll see why very soon, it also turns out that to get the insertion done properly, we sometimes need to take a left-leaning red link and temporarily make it lean right. Later on, we'll get it back to the left again, but anyway, that's a basic operation that we sometimes need. And so that's just the symmetric code to the code that we just did. Now X is h.left, and h.left is going to be x.right after the rotation. X's color is still going to be H's color, and H's color is going to be red. And the right rotation implements this. And again, that's going to maintain symmetric order and perfect black balance. We changed the way the red goes, but we didn't change anything about the black. Okay, that's a right rotation. Now here's the third elementary operation that we're going to perform. It's called a color flip. Sometimes during the insertion, we might wind up with a node that's got two red links coming out of it. That corresponds precisely to our temporary for node when we're doing 2-3 trees. And what we wanted to do with the temporary for node was to split it and pass the center node up to the root. Well, you can see from this structure that we're all set to do that. All we need to do actually is not change any links, just change all the colors. And so that is, we change the link from E to A and from E to S to be black. That essentially splits the for node. And then we want to insert the E into its parent. And we just do that by changing its link to be red. So that's flipping the colors. And that's the way we split a temporary 4 node in a left-leaning red-black tree. And again, that's just flipping colors. Doesn't change any links, so it still, of course, maintains symmetric order and perfect black balance. So those are the 3 basic operations we're going to use: rotate left, rotate right, and flip colors. So the basic strategy is, with those operations, maintain one-to-one correspondence with 2-3 trees when we do insertions. So here's an example. If we want to insert C into this red-black tree, which is a representation of this 2-3 tree, then C is going to be less than E, greater than A, so it'll get added as the right link of A. And every time we add a node, we just create a red link to its parents, and so that's changing the 2 node into a 3 node. In this case, it's a 3 node that's oriented the wrong way, so we need to do a left rotate. After we do the left rotate, we have a legal left-leaning red-black tree, and it exactly corresponds to that 2-3 tree. So the insertion of C gives us exactly what we'd want, the correspondence with the 2-3 tree. And we have to work through other cases that can arise, but there's not too many, so we'll work through them. And we have the basic operations: left rotate, right rotate, and flip colors. All right, so first warm up, insert into a tree with exactly 1 node. Well, if it goes on the left, then we just make a red link and add it on, and we're done. If it goes on the right, then we attach a new node with a red link on the right, but we have to rotate it to the left to make a legal 3 node. So that's insert into a tree with a 1 node and make it a tree with 2 nodes. And that one generalizes to help us insert into a 2 node at the bottom. So we do the standard VST insert, color the new link red, and then if that new 3 node happens to lean right, rotate it to the left. That's the case that we just did. So now let's look at a second warm-up. So say we have just 2 nodes in the tree. So we have 2 nodes, and that means it's a single 3 node. Then there's 3 cases. So one is that the new one is larger than both of the keys. If that's true, then we attach the new node with a red link as always, and that gives us a temporary 4 node. And what we want to do is split that 4 node, and in this case, since we're at the root, that's all, so that just flips the colors. Now the color of the root in our code would temporarily turn red and then would turn it black again. So that's inserting into a tree that's a single 3 node, a node that's larger than both of them, a key that's larger than both of them, and we wind up with a 4 node. But let's look at the other 2 cases, and understanding these is crucial to understanding the whole algorithm. Let's say the new key is smaller than both of the keys in our 3 node. Well, we attach a new link at the left of the smaller node, and now we've got to find BST, but it has 2 red links in a row. And that's something that's not allowed. So what we're going to do is we're going to rotate the top link to the right. So that puts B at the root, and now it's got 2 red children. It reduces it to this case, and we flip the colors, and we have a single 4 node, a red-black tree that's got 3 2 nodes and no red links. Same situation as before. So we had a single temporary 4 node, and we split it up into 2 2 nodes connected to a 2 node. And then, so that's the case when it's smaller. Now we have to look at the third case, which is when it's the new node is inserted is in between and comes out at this link here. Again, we just add a red link, and now we have a BST with 2 red links along a path connected to A, and that's not allowed. In this case, it's a bit trickier to fix the situation. What we do is we rotate the bottom link left. And that gives us this, and reduce it to the other situation that we had before. And then we rotate the top link right, and then we flip the colors. So this one we use all three of our operations: rotate left, rotate right, and flip the colors. And that gets us an insertion into a tree that has, from a tree that is a single 3 node to a tree that is 3 2 nodes containing 3 keys. So that sort of operation is going to work in a big tree when we insert into a new 3 node at the bottom. We do the standard BST insert, color the new link red. Then we do the rotations that we need, either 1 or 2 rotations to balance the temporary 4 node. And then we flip colors to pass the red link up 1 level. And then we might need to rotate to that and to make that one lean left. So for example, if we insert H into this tree here, it comes off as the left link of R. So that gives us a temporary 4 node that's not balanced. So we need to rotate the link from S to the right. And that gives us now a temporary 4 node that is balanced. And again, these are all local transformations. It's not changing the rest of the tree. Now we flip colors, and that gives us a good red-black tree, except that one red link that we just made is leaning the wrong way. So now we need to rotate left. And then once we've done that, now we have a legal left-leaning red-black tree. So that's a insertion into a 3 node at the bottom. So here's another one that involves, remember we passed that red link up. If that gets passed up to a 3 node, then we have to continue moving up the tree and just treat it in the same way as we just treated inserting at the bottom. We have a new red link appearing into some 3 node. There's the 3 cases that could happen. And here's an example. So say we're inserting P into this left-leaning red-black tree. It goes to the right of M, so we get a temporary 4 node that's got 2 red links. Both children are red in that thing, so we want to flip the colors. We flip the colors, and now our temporary 4 node is up higher in the tree, but it's not balanced, so we're going to have to do 2 rotations to make that balanced. First one is to make the bottom link left-leaning, and then the second one is to make the top link right-leaning so that we can have the temporary 4 node balanced. And then the last thing we do is flip the colors, and now that's the result of that insertion. It's a bunch of transformations, but they're all simple using our flip colors or left or right rotation. And that one happened to be at the root. If that red link were way down in the tree and there were another 3 node above it, we might have to do it again. Again, exactly as would happen in a 2-3 tree. So let's do a demo of constructing the red-black BST from our standard set of keys. So we start with a single key, and now if we want to insert E, it goes to the left, that's fine. That's a legal left-leaning red-black tree. A would go to the left of E, 2 lefts in a row, so we have to rotate S right, and then we have to flip the colors. And that's a legal red-black BST. So now if we insert R into this one, then it goes on a red link to the left of S, and that's fine, it's a red-black BST. And now if we insert C into this one, it goes less than E, greater than A. It's a red link connecting A and C, but it's leaning the wrong way, so we have to do a left rotation. Legal red-black BST. We want to insert H, that goes to the left of R, 2 reds in a row, rotate the top. Rotate the top, our temporary 4 node is balanced, flip colors. Now we have a 3 node, but the red link is leaning right, so we have to rotate. And then now we have a legal red-black BST. Insert X into that one. It goes to the right of S. That's leaning the wrong way. Rotate left. Insert M into this one. It goes to the right of H, leaning the wrong way. Rotate left. Most of the operations are simple ones like this happening at the bottom. Insert P. That goes to the right of M. That makes M a temporary 4 node that happens to be balanced, so flip the colors. Flip the colors. Now we have a temporary 4 node that's out of balance, so we need a double rotation. First rotate E to make that link point lean to the left, then rotate R to bring the temporary 4 node into balance, and then flip the colors. And that's a legal red-black BST. Insert L into that one, goes to the right of H, leaning the wrong way, rotate left. And that's an example of building a red-black BST from our standard set of keys. Now we're ready to look at the implementation of the code for inserting into a left-leaning red-black tree. And the key to understanding this code is to realize that the same code handles all of the cases. The way that it works is we're always reducing one case to another. We get this most complicated case. We did a left rotate on the bottom node, and that transformed it to this case where they're both leaning left. And then we did a right rotate on the top node, and that transformed to the case where our temporary 4 node is balanced, and then we flip colors on that. So for a particular insertion, we can take advantage of this reduce one case to another in the way that we're moving in the tree to get everything happen with just a few extra lines of code in our standard binary search tree. So in gray is our standard insertion code for binary search trees. Remember, we took some pains to think about the recursive implementation where when we go down a link, we replace that link by whatever the recursive routine gives us back. And that strategy is going to pay off in giving us really simple code. Because in this implementation for left-leaning red-black trees, we're going to return the link whenever we're done, and then that'll get that link installed up in the node above, whether it be left or right. Typical implementations of red-black trees that do not use this recursive strategy wind up having lots of cases depending on whether left or right, or double rotate to the left or double rotate to the right. I can be critical of this code because my own code was this way for the first 3 editions of the book. It's only in this edition that we figured out how to make the code this simple. Okay, so what are the things that have to be done? Let's just check. When we insert a new node, all we want to do is create a new node with the associating the given value with the given key as before, but now we just make that node red. So that's adding a new node with a red link at the bottom, inserting that into whatever 2 or 3 node it's attached to. And then we do the comparisons as before, and that's all fine. Now, when it's returned, then that's the point at which we're going to check whether the links are leaning to the left as they're supposed to, and whether or not there are any double links or not. So the first thing is if is red h dot right and not is red h dot left. So that means h is h dot right is red. So that means that the right link of h is leaning the wrong way. So h is a 3 node leaning the wrong way. So we just rotate left h. So whenever we find a right link, we're sitting on a right red link, we just rotate it left and return that. So that would be, in this case here, would rotate it left and reduce it to that one. Or in the case when we're just inserting a new node and it turns out to be the right red link attached to a black one. So that handles that case. Now, if h.left is red and h.left.left is also red, that's this case here, where we have two left-leaning red links. Then in that case, we just rotate the top one right, and that brings us to this one. So notice that we're in this case, we do this rotation first, we're on this node, and then that returns and we come up to deal with the situation on this node after the return, and then we do that rotation. And then after that rotation, or if there were no rotations at all, if the insertion happened over here, then we test and flip the colors. It's a little mind-bending at first because of the recursive structure, but it won't take you long to convince yourself that this little bit of extra code completes the implementation of left-leaning red-black trees. It's quite remarkable, actually. So let's look at a visualization. This is a balanced tree getting constructed in the worst case, where everything that comes in is in ascending order. A regular binary search tree would just be all strung out in a single line and would have quadratic time for this input. But a left-leaning red-black tree actually, whenever it becomes a power of 2, is completely balanced, as you can see from this example. Even though they came in ascending order, the tree winds up being perfectly balanced. And what about descending order? Well, it's left-leaning and the process is a little bit different. And sometimes the left path can get long, but not that long. The worst that can happen is that it alternates red and black. And then after it gets to that worst case, it also winds up being completely balanced when we have a power of 2. Interesting to think just about this case and to prove to yourself that it's always going to be perfectly balanced when it's descending. This is just for random insertions. The tree stays very balanced. It's guaranteed that the longest path, which is alternating red and black, can be no more than twice as long as the shortest path, which is all blacks. And so in this case, the longest path is 10, and the average path is 7 for 255, very close to log base 2 of n. Easy to prove by correspondence with 2-3 trees that the height is guaranteed to be less than 2 log base 2n. Every search in a left-leaning red-black tree is guaranteed to take less than 2 log base 2 of n, because every path's got the same number of black links, so you never have 2 red links in a row. And actually, in typical applications with any kind of randomness, or even if there's a lot of order, it's difficult to find situations, orders of keys that build trees that height is bigger than actually 1 log n. In real applications, it's very close to fully balanced all the time. So that completes our summary for symbol table implementations. With red-black BSTs, we have full code. It's the regular BST code with a couple of lines adding the calls on the basic operations to rotate right, rotate left, and color flip, and we get guaranteed logarithmic performance. Not just for search, insert, and delete. Well, delete code is a bit more complicated, but it's on the book site and in the book. But also, since it's the compare to interface, and since it's a binary tree representation, all the other comparable operations, extended operations for ordered symbol tables are going to be implemented and take time proportional to log in. A lot of people ask, why did we use the name red-black? We invented this data structure, this way of looking at balanced trees at Xerox PARC, which was the home of the personal computer and many other innovations that we live with today, including graphic user interface and Ethernet and object-oriented programming and many other things. But one of the things that was invented there was laser printing. And we were very excited to have nearby a color laser printer that could print things out in color. And out of the colors, the red looked the best. So that's why we picked the color red, to distinguish red links, the types of links in 3 nodes. So that's an answer to the question for people that have been asking. Now here's another war story about red-black BSTs. As I mentioned, they're widely used, and there was an example not that long ago where a telephone company contracted with a database provider to build a database that could store customer information. And the provider implemented the database using red-black BSTs for search and insert. Now, our original paper on red-black trees was the way the paper was laid out. It turned out that the delete implementation happened to be placed after all the references, so a lot of people didn't see the delete implementation. And also, we didn't have the simple left-leaning representation, so it was more complicated and involved a lot more cases, and so usually not all the cases were put in the textbooks. So people found deletion more difficult. In fact, that's what led me to analyze the situation and come up with the left-leaning variant. So what they did in this implementation was they just put in regular Hibberd deletion in the binary search in the red-black BST, not the deletion algorithm that's guaranteed to keep the constant black height all the time. And so but they still thought that it should be balanced and it shouldn't matter much. And they had a complex error recovery process that got triggered if the height limit got too big. And they would rebuild the whole tree, and then because of the way they did this deletion, well, the end of the story was that they had extended, the client had extended outage because the implementer didn't use the full algorithm. And there was a lawsuit and some legal testimony. And happy to report that it was clear that Hibberd deletion was the problem once the expert analyzed it. And the expert witness, who's a colleague of mine, said if implemented properly, the height of a red-black BST with n keys is at most 2 log n. So that's the story of red-black BSTs, guaranteed logarithmic performance for all symbol table operations. Welcome back. Today we're going to take a look at a number of interesting applications of symbol tables and the binary search tree data structure to address problems with processing geometric data. So let's take a look at it. The idea is that we're going to be talking about geometric objects, not simple keys like strings and numbers. So here's an example. So say your geometric objects are points in the plane, and you specify a rectangle that's oriented with the horizontal vertical axes. And you might want to ask which points are inside the rectangle, or how many points are inside the rectangle. Or maybe what you're processing is rectangles. You have a set of rectangles, and we want to know which of these rectangles intersect, or how many rectangle intersections are there. These are interesting problems that have lots and lots of applications, from computer-aided design to games and movies, And also in abstractions such as databases and other situations where you might have multiple keys or multiple dimensions. And it's a very interesting extension of the ideas that we've looked at for symbol tables for all sorts of familiar applications. And surprisingly, binary search trees and the associated algorithms that we've looked at are going to provide very efficient solutions to a number of important problems in this area and really have enabled new developments and new technology in all of these kinds of applications. So to get started, we're going to look at a simple problem called one-dimensional range search, and it really forms the basis for what we're going to do. It's a little bit of an extension of the ordered symbol table API that we gave before. And we're going to have the operations range search and range count. So one-dimensional just means we have one key. So we'll insert a key value pair as before. And what we want to do is be able to search for a key and the value associated with it. We want to be able to delete. But then we want these operations range search and range count. So find all the keys that are between two given keys, or give how many keys are there between two given keys. So for this example at right, we have insert a number of keys, and we're just showing them in sorted order. But then you might say, well, how many keys are there that are between G and K? In this case, there's just two. And then the client might say, well, what are those keys? You want to be able to return them. And this is a very common operation, say, in databases. You want to return how many taxpayers have salaries between 1 million and 10 million, and then which ones are there, and so forth. So range searching is a very important fundamental operation. Now in geometric interpretation, we just think of the keys as points on a line. And so the key values, are just specified as points on a line. We might convert the letters to numbers, or keys might be numbers. And then what we're looking for is to find or count the points in a given interval in one dimension. So how we're going to implement that? Well, this is a basic problem that is very similar to our symbol table problem. We might consider keeping the things in an unordered array. Just put them in an array, and then, well, insertion is fast. We just add it to the end of the array. We might have to use resizing to make the array grow. But this is unattractive because for large numbers of keys, in order to count the keys that fall within a given range, you have to go through all the keys and test whether they're in the range or not, and to return them the same way. So take linear time for a large number of keys. If you keep the things in order, like in a binary search situation, then to insert, in order to keep it in order in an array, you might need to move the larger ones over one position and so forth. Our elementary implementation of binary search, when we did symbol tables, did this. So the insertion time might be linear, but then you can use binary search to look for the two endpoints. It's only going to take time proportional to log n, and then from that you could figure out how many keys there are, or return them all between the index of the lowest one in the range, the index of the highest one in the range. So those elementary implementations are not acceptable for large numbers of keys because they have the linear time operations. So what we really want is to have time proportional to log n for insert and for counting. For range search, of course, we have to touch every key that we return, so the running time is going to be proportional to the number of keys that match. But anyway, those are reasonable goals, and they're easy to achieve. So, for example, what about one-dimensional range counting? Well, what we're going to do is just keep the keys in a binary search tree. We looked at the implementation of the rank function for binary search trees, where for every key we can compute how many keys are there that are strictly less than that key. So in this case, the rank of E is 2 and H is 3 and so forth. So in a binary search tree, those rank numbers go in increasing order as we do an in-order traversal. And that's easy to compute. Either keep that rank tree as a field or keep a field which has the size of the tree, and it's easy to compute the rank from that. So how many keys between, say, E and S? Well, 1, 2, 3, 4, 5. It's actually just the difference between the ranks plus 1 if the high entry in the range query is in the table and not plus 1 everywhere. So there's the same number of keys between E and S as there are between E and T. 5. Between F and T, there's only 4. So that's a really 1D range count is a very easy computation to perform in log time with a binary search tree. The number of nodes examined when we do a search is the length of the search path to low plus the length of the search path to high to find their ranks, and that's going to be time proportional to log n. So in range search, well, we just do a recursive search, and to find all the keys between low and high, you look in the left subtree if any of them could fall in the range. You look at the current node, and you look in the right subtree if any of them could fall in the range. And it's easy to tell whether any of them could fall in the range by just checking whether the range overlaps the root or not. So if we're looking for all the keys between F and T, then we have to look at both subtrees of the root S, but we don't have to look at the left subtree of E because all of those are less than E and therefore are less than F, so we don't have to look there. But otherwise, it's a simple modification of recursive tree search to find all the keys. And it's easy to see that the running time of that is going to be proportional to the number of keys returned plus log n. So that's one-dimensional range search using binary search trees. Okay, next we're going to look at another extension of geometric algorithms to process slightly more complicated objects, and then we'll see an important application. And this is called interval search. So now, instead of points, our data is intervals. So this is, we'll start with one dimension as before, and right away I can see that it's a more complicated problem than we've been dealing with. So we want to support the following operations. We want to be able to insert an interval. So an interval is just a left endpoint, right endpoint of one-dimensional data, or points on the line. We want to be able to insert an interval, search for an interval, delete an interval, but the main thing is we want the interval intersection query. So given a query interval, we want to find all intervals in the data structure that overlap that interval, or find any interval. We'll start with that simpler problem. So how are we going to support that? So this is the API in Java code. We have intervals, so instead of one key we have two, which is the left and right endpoints of the interval for put and get, and then we have delete, and then we're going to have the intersects. And again, to simplify the code, we're going to make the non-degeneracy assumption that no two intervals have the same left endpoint. That's easy to fix, but we don't simplify the code. So now we'll look at a data structure called an interval search tree that helps to solve this problem. It's an extremely simple algorithm, but surprisingly complicated to understand, so we'll go slowly. So the first thing is, what we're going to do is use the left endpoint of each interval as the binary search tree key. So our nodes store intervals, but we only use the left endpoint as the key. So this is the binary search tree that's built from those 6 intervals in our example. 17, 19's at the root, so everybody with a left endpoint less than 17's to the left, and everybody with a left endpoint greater than 17's to the right, and so forth. So that's a binary search tree built from those intervals. So that's easy. Just build a binary search tree. Just use the left endpoint as the search key. But we're also, in each node of the tree, we're going to store not just the interval, but we're going to store the largest endpoint in the subtree rooted at that node. So at every node, we're going to store the maximum endpoint in the subtree rooted at that node. So at the root, the maximum endpoint, or the rightmost point covered by an interval, is 24. So we store 24 at the root, and of course at the right subtree. In the left subtree, the max endpoint is at 18, so that's what we store for the associated data with the node to the left of the root, and so forth. We're going to have to, that's data that we're going to have to maintain when we do an insert, and it's data that we'll use when we're doing an interval intersection search. So let's take a look at a insertion into an interval search tree with a demo. All right, so the insertion algorithm is pretty simple. We do the BST insertion, it's just that we have to do that update of the maximum in each node on the search path. So to insert 16, 22 in this tree, well, we use the left endpoint as the search key. 16 is the left endpoint of our insert interval. We compare that with 17 and therefore go left. Now 16 is bigger than 5, so we go right. Now 16 is bigger than 15, so we go right. And that's null, so that's where we insert our new interval. So now we're going to go back up the tree, and for every node that we encounter, it could be that our right endpoint of our interval is bigger than what was there, so we have to check all the way up the path the maximum in each node on the path. So we have to check each node to see if 22 is bigger, and for the 3 nodes to the left, it is bigger than 18. For the node at the root, it's not, that stays to be 24. So it's just binary tree insertion, but then after the insertion on the way up, we go ahead and check if the maximum that we have is bigger than the maximum there and update it if necessary. So easy to code. All right, so now about how do we do a search. So the search is definitely more complicated and kind of mysterious, but let's look at the rules for search in an interval search tree. All right, so now we're going to look to see if we have an intersection. We want to find just any interval that intersects this query interval 23, 25. We're not going to try to find them all. We'll get back to that in a minute. Try to find any interval that intersects our query interval. So let's see what we have to do. So first thing is, if at the root we have an intersection, then we're done. We just return. In this case, 23, 25 does not intersect 17, 19. So we have to go down the tree somewhere. So left subtree is null, go right, okay. Otherwise, we have to check whether the max endpoint in the left subtree is less than the low point in our interval. And it's easy to see, well, if that's the case, then we're not going to find an intersection in the left. The maximum endpoint in the left is 22, and we're looking for 23. We're not going to find anything there, so we just want to go right. So in this case, we'll go right. 22 to 23, no intersection on the left, so we go right. And now we do find an intersection. 21, 24 does intersect with 23, 25 because 23 is in the middle there. So we find an intersection. Now, on the other hand, let's say that we're looking for 12, 14. No intersection. All the algorithm says is that if you didn't go right, go left. So let's go left. In this case, so we weren't able to show that there was no intersection on the left, so we're going to go left. In this case, we compared 12, 14 to 5, 8. So now we apply the same rules. Does it intersect? No, it doesn't intersect. Should we go left? Well, no, the maximum endpoint in the left node is 8, so we can't have an intersection there, so we're going to go right. Compare 8 to 12 and go right. So now does 12, 14 intersect 15, 18? It does not. So there's no intersection. So now what do? Should we go left? No, the max endpoint on the left is 10, so we shouldn't go left. We're going to go right. Does 12, 14 intersect 16, 22? It does not. Now the left endpoint's null, and so we're just going to go right, and there's no intersection. So in both cases, we just went along one path in the tree to determine whether or not there was an interval or intersection. Let's look at one more example, 21, 23. Let's see, 21 through 23 to 17, 19. They do not intersect. So now what are we going to do next? We're going to compare the left subtree, and it's not. 22 falls within our interval, it's not less than ours. So there might be an intersection there, so we better go to the left. So we do go to the left. Now we compare against 5, 8, and there's no intersection. So now we're going to go left or right. Well, we're going to go to the right because the max endpoint in the left subtree is 8 and our interval is 21, so no intersection on the left, so we're going to go right. Intersection 21, 23, 15, 18, they do not intersect, so now do we go left or right? Again, 10 is less than our left endpoint 21, so we better go to the right. And now 21, 23 does intersect 16, 22, so we return an intersection. Again, one path through the tree to determine an intersection. So from those rules, you can see that the amount of code required to implement this intersecting interval is extremely low. We just check for an intersection. If we find it, return. If left is null, we go right. Otherwise, if the max is less than low, we go right. Otherwise, we go left. It could hardly be simpler. Really amazingly simple and efficient algorithm. We should convince ourselves really that it always works, and so we'll spend just a moment on a short proof. So let's look at the cases that could happen. First thing is, if the search goes right, then there's no intersection in the left. And that's easy to convince ourselves of that just from what we did in the demo. Of course, if the left subtree is empty, there's no intersection there. But if the max endpoint in the left subtree is less than low, that means every interval in the left subtree has a max endpoint less than low, and so therefore it can't intersect. So if you go right, there's no intersection in the left. Any possible intersection would have to be in the right. And then the other point is that if you go left, then either there's an intersection there or there's no intersections at all. Let's suppose that there's no intersection, and that's equivalent to saying if there's no intersection in the left, then there's no intersection in the right. So let's look at if there's no intersection in the left. Since we went to the left, and then we've got low less than max. But for any interval in the right subtree, it's got to appear after low because since there's no intersections in the left subtree, high has got to be less than C because they're sorted by left endpoint. And then that means that C's got to be less than A if A's in the right, so then therefore there can't be any intersection in the right either. No intersection in the left means no intersections at all. So those two cases is enough to show that this algorithm finds an intersection if there is one. And the other thing we can do with this is just use a red-black BST to guarantee that we solve this in time proportional to log n. So insert, find, delete, and find any interval that intersects all take time guaranteed proportional to log n. And if we want to find all intervals, we just have to run the algorithm for each interval that's until we come up against no intersection. So it'll take time proportional to r log n if there's r intervals that intersect. The theoretical best that you could possibly do would be r plus log n, but in practice r log n is quite efficient. This is an easy and very efficient algorithm to solve this interval search problem. And as we'll see, this algorithm is applicable to an important application that we'll see in a minute. Now we're going to look at KD trees, which is an extension of BSTs that allow us to do efficient processing of sets of points in space. And it's very flexible and very useful in lots of applications. So now we're going to extend the API to talk about two-dimensional keys. So that's just, you can think of two-dimensional keys as points in a two-dimensional geometric space. So we're going to talk about insertion and search. We want to talk about deletion, and then range search and range count. So we want to be able to insert and delete points. You can think of a two-dimensional key as a point in a two-dimensional space. And then we want to be able to find all keys that lie within a two-dimensional range. That's a rectangle, as I mentioned at the beginning, or count the number of keys that lie in a two-dimensional range. So again, the geometric interpretation is the keys are points in the plane, and we have a range, 2D range is a rectangle or is oriented to align with the horizontal vertical axes. And we want to be able to find or count the points in a given rectangle. And this one has many, many applications, and we'll talk about some of them later on. And even if it's not points in the plane, just databases, you might ask for all the people with incomes between 1 million and 10 million who are between 40 and 50 years of age. And this kind of algorithm and data structure would be useful for that kind of situation too. So how are we going to solve this problem, implement this API? We build a data structure containing points that can efficiently support range searching and range counting. Well, one easy way to do it is to just think about dividing space into a grid of squares. So we'll pick a parameter m and divide space into an m by m grid of squares, and then process all the points and make a list of points that are contained in each square. We can use a two-dimensional array to directly index relevant squares. And for insert, you just take x, y, figure out which square it belongs to, simply divide by both coordinates by m, and look in the two-dimensional array, and just add the point to the list for the corresponding square. And then range search is only find the squares that intersect the query and process the points in that square. And depending on the value of the parameter m, you have a space-time trade-off. The amount of space required is m squared for the grid, plus n. You have to have a linked list element or whatever for each point. And then the time, though, gets divided by m squared. Your number of points m are spread out over the m squared different squares. And so on average, you examine n over m squared points per square. So you don't want to make m too big, be too much space. You don't want to make m too small, be too much time. So what we want to choose is the square size that would best balance these two needs, and then it's easy to see that what you should choose is m to be about square root of n, so then your space is within a constant factor of n and your time is constant. So if the points are randomly distributed, then this is ideal. It takes this linear time to initialize the data structure, and to insert and search, it takes constant time per point in the range. And this is absolutely a fine method that is not that difficult to implement in the case that the points are evenly distributed. Unfortunately, it's usually the case that in geometric data that the points are not evenly distributed. And so a well-known phenomenon known as clustering that says that the points aren't going to be evenly distributed all over the whole thing. In the case of the grid implementation, they might all fall in the same square. And so the average list length is short. This is like what we encountered with hashing. If you take all the points in one square and 0 in all the rest of them, your average is still n over m squared, but they're all in that long list, and you're going to have a slow algorithm if it's based on this. So we need a data structure that more gracefully adapts to the distribution of the data. And again, it's well known that most geometric data has this kind of problem. So for example, here's some data which is cities in the US. It's got 13,000 points, but if you tried to use the grid implementation for this, you find that half the squares would be empty and half the points are in just 10% of the squares. So the clustering in the data is going to make the implementation inefficient. We need to adapt to the data, and this is very, very typical in geometric data, particularly in higher dimensional data, as we'll see in a minute. So people have developed all different kinds of methods for adapting in this way, and what we're going to look at is one of the most widely used, which is basically to use a tree to represent a recursive subdivision of the plane of two-dimensional space. It's going to be recursive. It's going to be based on the points, the way in which we divide into half planes. And it's one of many different algorithms that have been studied for this, but again, it's a simple one and widely used. So for example, if you've played the game Doom or used a flight simulator, these types of graphical simulations and animations are made possible only through the use of space partitioning trees like 2D trees and quad trees, and also in all different types of scientific data processing. These things are extremely important. Whenever you're processing geometric data, you're doing some kind of geometric search. You know, where's the closest thing? How am I going to find the closest thing efficiently? What things are nearby? And so forth. So rest assured, these types of algorithms lie at the heart of any program that you use that is involving a lot of geometric data. So those are just two examples. So let's look at how it looks now. So a 2D tree is, again, it's going to be a data structure based on a bunch of points that's going to facilitate efficient data processing of these points. So just as we do for symbol tables where we take keys, now we're going to take points and we're going to build a data structure based on these points. And the idea is to build a tree that corresponds to recursively partitioning the plane. So arbitrarily, our first point, we're going to divide the plane into two parts based on a vertical line through that point. So now in the tree on the right there, all the points that fall to the left of the first point are going to be on the left, and all the points that fall to the right of that first point are going to be on the right. But then we get to the next point, we'll switch and we'll partition on a horizontal line. So now our second point in the tree, the left subtree corresponds to everybody below that horizontal line, and the right subtree corresponds to everybody above it. Similar, if our third point comes on the left, again we'll partition according to the horizontal line through that point on the left. So if we go left and then left, that means all the points to the left of 1 and above 3, so the square in the upper left is represented by that node in the tree. Again, now when we go to one level below, we switch again to vertical, alternate between horizontal and vertical partitioning of the plane. So it's a regular binary search tree, but it's got this interpretation based on the geometric data where we switch which key we use for the comparison, the x-coordinate or the y-coordinate at each level. And that corresponds to this partitioning of the plane. So now 5 comes in, that's to the left of 4 because it was partitioned on a vertical, and 5 is going to partition on a horizontal. And this is a simple and completely well-defined partitioning of the plane corresponding to a binary tree. Now the 9th point, well, it's to the left of 8, above 2 to the left of 8, and then corresponds to horizontal partitioning. 10th point is to the right of 1, it's below 2, so we go to the left, and it's to the right of 7, so we go to the right. So that's a way to build a binary tree corresponding to a partitioning of the plane. And it's really the same as a binary search tree, it's just that we alternate which coordinate we use as the key. At the even levels, we think of a vertical line, and the left subtree is all the points to the left, and the right subtree is all the points to the right. On odd levels, we use a horizontal line, and the left subtree is all points below, and the right subtree is all points above. And the code for this is the same as for binary search trees. It's simply which coordinate we use for the comparison. That's the only difference. So that's 2D tree implementation. So now what about solving a problem like this range search problem for a 2D tree? So now we have a query like this green rectangle, and what we want to find is all the points in the data structure that fall within that rectangle. Well, we're going to use the 2D tree represents our points, and we're going to use the structure and definition of that tree to go ahead and help us find the points that are in the rectangle. If the root node lies in the rectangle, then we're done. We can return that point, but we have to look on both sides to look for more. But if the rectangle lies to the left of the root node, then we only have to look in the left and so forth. So let's look at how this works in a demo. All right, so we're going to try to find all the points that are contained in that green query rectangle. So first thing is to check if our rectangle contains the node at the root. In this case, it doesn't. So since it's to the left of the splitting line at the root, we only have to search in the left subtree. Now we search the left subtree. We're going to check if it contains 0.3. It does not contain 0.3, but now which subtrees do we search? In this case, the rectangle intersects our splitting line, so we have to search both subtrees, both above and below. So first we search the left subtree, that's the one below. Does it contain 0.4? No. It's to the left, so we're going to have to search the left subtree of 0.4. And so we search the left subtree and we check if it contains 0.5, and it does. That's the one that we return. It also intersects the splitting line, so we have to search both the subtrees. In this case, they're both empty. So we're done with that, but now we have to go back and we have to search the other subtree of 0.3. That's the above, so now we check is 0.6 in the rectangle. In this case, it's not, and it's to the left, so we have to search the left subtree of 0.6, and that one's empty, and now we return, and we're done. So we don't always go down just one branch. If our splitting line hits our rectangle, we have to go down both branches. But still, this is a very efficient algorithm. Particularly think about the rectangle being small. It's going to be not that different than a regular search in a binary search tree. All right, so what about the analysis of how long is this going to take? Well, again, a typical case, a rectangle's small, that we're only going to examine really a path of the tree, maybe a couple of other nodes along the path, and the running time will be proportional to the number of points returned plus log n. With geometric data, the worst case can be bad. So like all the points could be arranged in a circle, all different types of problems might occur. And with some difficulty, it's possible to prove that even if the tree's balanced, you can get a worst case proportional to square root of n. So analysis of 2D trees is a bit beyond our scope. But for many practical applications, they're easy to implement and worth using. Let's look at another, using 2D trees to solve another problem, the so-called nearest neighbor search. So now, instead of a rectangle, we have a query point, and our goal is to find the closest point to that point. So in this case, our query point is over here in green, and our algorithm's going to want to return 0.5. That's the closest one to the query point. So let's see how that looks in a demo. So again, we start at the root, and what do we want to do? Well, we're going to check, whenever we're at a node, it represents a point, so we're going to check that point. And we'll compute the distance from that point to our query point. And if that distance is less than the best found so far, then we'll keep that as the champion. So the first point, that's the closest we found so far to the query point, so we'll save number one as the distance. And we'll only worry about the possibility of finding something closer than that. And so just using that distance, we recursively search any part of the tree that could contain a closer point. And so that's what we'll continue to do. So in this case, the query point is to the left of the splitting line, and we'll always go towards the query point first. So in this case, we have to search both. There might possibly be a closer point than one over in the right. If you come like straight across, there might be a closer point. We're going to have to look at both as far as we know now, but we'll go towards the query point and see if we can find something closer. So in that case, now we go to root node point 3. Compute the distance of that point to the query point. It's closer, so we update 3 to be our new champion. And so now we're only going to look in parts of the tree that could give us a point that's closer to our query point than 3. Notice already that'll mean when we get back to point 1, we won't search the right subtree because there could be no point on the right subtree the right of this splitting line that's closer to the query point than 3. And so that idea of getting closer and closer to the query point is going to cut out different parts of the tree as we process. But anyway, starting at point 3, as far as we know, we're going to have to look at both subtrees. So sometimes we look at both subtrees, but as we get closer and closer, we only look at one. So let's look at point 3 now. Again, go towards the query point, so we'll go to the top first, and that takes us to 6. 6 is not any closer than 3 was, so that's not going to update our champion. And so we'll search 6's left subtree, which is empty, and then its right subtree. Well, the nearest neighbor can't, we don't have to go down the right subtree of 6 because you can't have a point in that rectangle that's closer to the query point than 3. So now we can return from that, and now we have to look at the bottom subtree associated with 3. And so that takes us to 4, and that one is not closer, so we still have 3 as our current champion. So now we'll search the left subtree of 4 first, because the query point is to the left of that splitting line, and that takes us to 5. And 5 is our new champion, so that's the closest point that we know about. Could there be a node that's closer to 5, to our query point than 5 in the right subtree of 4? We have to go above, sorry, to look at the top subtree associated with 5 and find that it's empty. And now we're back at 4. Do we have to search the right subtree of 4? No, because there can't be a closer point than 5 in the right subtree of 4. So we're done with 4, and we return to come to 3. And now we search the, supposed to search and return from there. We now are at 1, supposed to search the right subtree of 1 next, but we can prune that. Nearest neighbor couldn't be in there. So then we're done, and we found that the nearest neighbor is 5. And this is going to be very efficient because as we get closer and closer to the query point, we're cutting out all the subtrees that are away. And again, in practice, the running time of this algorithm is going to be close to logarithmic. So in typical cases, the running time of nearest neighbor search in a 2D tree is going to be proportional to logarithmic. It is possible to concoct cases where you're going to have to examine all the points. For example, if they're all arranged in a circle and your query point's in the center or something of that sort. But for typical data, it's very efficient. Now we're going to look at an application where we simulate a phenomenon in nature. And this is what kind of patterns do things like starlings and geese or cranes or fish or fireflies, how do they flock together? And we'll look at a simulation that corresponds to that.
And then, when the moment is right, they behave in a way that should be impossible. And it happens every day, right through the winter, just a couple of miles from my doorstep. How good is that?
So there's a simple model developed by Craig Reynolds a while ago for simulating this situation called the Boyd. And the idea is to use 3 simple rules to you get something very close to this complex flocking behavior. So you have collision avoidance, where you always try to point away from the k nearest Boyds. You have centering, where you try to point near the center of mass of the k nearest Boyds, and velocity matching, where you update your velocity to the average of the k nearest Boyds. And that algorithm works like this. So as that example shows, 2D trees are extremely effective in quickly processing huge amounts of geometric data. And what's more, it expands to more dimensions. With a very simple modification, we can take a 2D tree and create a data structure known as a KD tree, which even works for k dimensions. And the idea is, even if there's k dimension, what we'll do is recursively partition one dimension at a time. So that's called a KD tree. And we use the same idea as for 2D trees, but instead of cycling through just horizontal vertical, we cycle through however many dimensions there are. So it's in 3 space, we use a plane and do above and below, and then simply cycle through the dimensions. At level I, we put on the left the points whose ith coordinates are less than p, and on the right we put the points whose ith coordinates are greater than p's. And at cycle through the dimensions at level I mod k, we just use that dimension of the point to do the comparison. The implementation is simple, except for the comparison, and we get the same kind of partitioning for 3-dimensional data, so we could do Boyds in 3 dimensions, or for databases with a large number of dimensions, you could do even much higher dimensional data and find nearest neighbors and do range searching extremely efficiently. It's a very efficient and simple data structure for processing k-dimensional data that's very widely used, and the whole idea is that data clusters, particularly in high dimensions. And also one point to make for this class is that this algorithm was discovered by an undergraduate in an algorithms class. So that's John Bentley, who discovered this while an undergraduate at Stanford. So it's a simple idea, but expert scientists were struggling with dealing with huge amounts of geometric data, and Bentley found this way to process it efficiently that's been widely used ever since. And in particular, just as another example, consider the idea of n-body simulation, which is a classic problem in physics. Where you've got n particles mutually affected by gravity, and basically the computation is based on computing the interacting force for each pair of particles. And so then there'd be mutual gravitational pull, and this is what happens with a large number of particles in a certain simulation, and people understand properties in the universe by coming up with doing these kinds of calculations and comparing against what's observed in space. Now, but the thing is, for each pair of particles, so if you have n particles and you have to do it for each pair, that's n squared. So the progress of scientific investigation is going to be affected by how quickly you can do this calculation for a large number of particles. There's a lot of particles out in the universe, and you can't do a quadratic calculation for large n. Another undergraduate in an algorithms class discovered this idea for n-body simulation, and that's Andrew Appel. And his idea was that if some particle is way away from some cluster of particles, we can treat that cluster as a single aggregate particle and not do the individual force calculation between our particle and every one of those in the aggregate, but use the center of mass, and you get a very accurate approximation to the end body doing that. And the algorithm that he used is based on 3D trees with the end particles as nodes and storing the center of the mass of the subtree in each node. And then to compute the total force traversing the tree, you have all the information that you need to complete the end body calculation, but in time much closer to n log n than to n squared. And that idea that you didn't need to take time proportional to n squared, but with a geometric algorithm like a 3D tree, you could get the time to n log n, that enabled all sorts of new scientific investigation. And it's an example of the use of algorithms to enable new research. So now let's look at a basic geometric data processing problem of determining intersections among a set of line segments. So it's called the orthogonal line segment intersection search, where the line segments are constrained to be either horizontal or vertical. And so suppose we have a large number of such line segments, and what we want to do is be able to find all places where they intersect. And as we'll see, this extends to a practical problem in a number of situations. In this case, there's 4 places where these lines intersect. So how are we going to be able to determine these intersections efficiently? The natural algorithm, or the naive brute force algorithm, is quadratic in time. So that is, for every line segment, you check whether it intersects with every other line segment. And again, as we know, such an algorithm is not going to be practical for huge numbers of line segments. Just to simplify our code in these slides, and it's often the case for geometric data processing, we have to worry about degeneracies, where lots of things have the same x or y coordinate. And just to simplify the code and to get at the main principles of the algorithms, we're going to assume that all the coordinates that we have are distinct, that we've pre-processed in some way to remove the ones that touch without intersecting. So the method that we're going to look at is the so-called sweep line algorithm. And the idea is to think of a vertical line that sweeps from left to right through the data, and to consider it as every time it hits some line segment as an event where we have to do something. So sweeping from left to right means we consider each x coordinate as an event. First thing is, if we hit a horizontal line segment, we're going to hit the left endpoint first. And so what we'll do when we hit the left endpoint is insert the y-coordinate of that line into a binary search tree. So we're going to keep track of y-coordinates in a binary search tree. So that's what's happening over in the right there. So now, again, sweep from left to right. What's the next smallest x-coordinate? In this case, it's the line number 1 there, and we'll remember its y-coordinate in a binary search tree. And then 2 and 3. So that's one kind of event that can happen as we sweep from left to right. Another kind of event is that we hit the right endpoint of a horizontal line segment. In this case, we hit the right endpoint of line segment 2. So at that point, the right endpoint of a horizontal line segment, we just remove it because we've processed that line completely. In this case, we didn't find any intersections. So left endpoint, insert the y-coordinate into a BST. Right endpoint, remove that y-coordinate from the BST. So the BST contains the y-coordinates of all the horizontal lines that currently might involve an intersection. And then the third kind of event is what happens when we hit a vertical line segment. Well, in that case, all we need to do is just do a range search for the interval of y endpoints. So any point that's inside that interval is going to represent a horizontal line segment that is an intersection. That's the basic idea behind the sweep line algorithm to find intersections in sets of horizontal and vertical lines. And it's actually a very simple algorithm, and it's very easy to see that the running time is going to be proportional to n log n plus the number of intersections returned, where there's n horizontal vertical line segments. And it's a couple of ways to implement it. One thing is you could sort according to the x-coordinates, or you could just put them all on a priority queue. And then, so that's going to take n log n for every one of the lines to process them all. Either n to build a priority queue and then log n to take the smallest off each time, or n log n for the sort. And then putting the y-coordinates into a binary search tree is, again, n log n, and same for deleting. Each point has to be inserted, deleted. There could be as many n as n in the tree for each one, so it's a total of n log n. And then the range search in the binary tree for each one of the range searches might take log n, might be as many as n, and then there's plus the number of points returned. So that's a quick sketch of the proof of this proposition. And with that 1D range search implementation, we get an efficient n log n 2D orthogonal line segment intersection algorithm. To finish up, we're going to look at the rectangle intersection problem. That's got important practical applications and uses the techniques that we've been studying so far. And it's a simple generalization of our line intersection problem. So now we have a bunch of rectangles. They're all oriented horizontal or vertical. And what we need to do is find all the intersections in that set of rectangles. And again, n could be huge in applications, as we'll talk about in a second. And the naive brute force algorithm involves checking each pair of rectangles for intersections. And what we want is a more efficient algorithm than that, as usual. And again, to keep the code simple, we're going to assume that all the coordinates are distinct. We don't have any equal lines we don't have to worry about. Whether we consider rectangles that touch to be intersecting and so forth. So that's the problem, rectangle intersection search. And this is historically an extremely important problem. In the 1970s, when we switched to very large scale integration for computers, we were switching from a situation where we were wiring physical devices together to a situation where we were essentially drawing the computer. And there were machines that would take drawings and return, and from those drawings, like this, make physical things that implemented computers with different layers and different physical materials interacting in different ways. Some things are wires, and some things are switches that are used to implement memory bits in computer logic. But the key point about it is that designing a computer became a geometric problem. And so people, to design new computers, would make huge drawings that just showed the lines that corresponded to the materials that had to be created to make the computer. Now, it was very expensive. You didn't want to have any bugs when you're making a chip. And there were various rules about what you can do on these drawings. And basically, these rules had to do with doing this orthogonal rectangle intersection search. You can't have lines that come too close to other lines. Certain types of lines can't intersect. need spacing between certain types of wires, and you wanted to, before you tried to make the physical circuit, to do this checking, which involved this orthogonal rectangle intersection search. And it was actually the case that the progress of faster and faster processors with more and more components was slowed because people were using the naive quadratic algorithm to do this design rule checking. And it's an example of Moore's law. So as we built a faster computer, say in 1970X, we needed to check in rectangles. But now, maybe a year and a half later, you have a computer that's 2 times faster, but you also want to build a bigger computer so you have twice as many rectangles to check. So you have 2n rectangles to check now, and your computer's twice as fast. So we get to use the faster and bigger computer to build faster and bigger circuits, but that doesn't help if you're using a quadratic algorithm. If you're using a quadratic algorithm and it takes you m days to check your design rules, and people were running these things on the order of days, then for the next computer it would take 2m days. It would take twice as long. And so people that were using quadratic algorithms were definitely held back. And it was Ed McWright at Xerox PARC who discovered interval search trees and the logarithmic algorithm that allowed us to sustain Moore's law and keep building bigger and bigger computers by changing this quadratic algorithm to a linear arithmetic algorithm. And let's see how it works. Really, it's a modification of the sweep line algorithm that we looked at for intersecting lines, but now we're going to use that for intersecting rectangles. Rather than using range search as our basic operation, we're going to use interval search. So now, every time the line sweep hits a rectangle, that corresponds to an interval. If it's the left part of a rectangle, then we put that interval into our interval search tree. So in this case, we put on 0, and then we put on 1, and then we put on 2. And that'll give us now 3 rectangles on our sweep line. And so now the question is, when we hit a new rectangle, we want to do an interval search to, if we're at the left, to check which ones intersect. And the interval search tree algorithm is going to tell us which intersections there are right away. When we reach the right, then we remove integrals and so forth. But with the basic interval search tree algorithm and the sweep line process that we've talked about, you can get the orthogonal rectangle intersection search problem solved in time proportional to n log n plus r log n, where r is the number of intersections. And typically in design rule checking, you wouldn't expect too many intersections. So again, just as with line intersection search, using a priority queue or a sort is only n log n for processing the x coordinates. And because interval search trees take log n for every operation, the insert and delete intervals is n log n total, and the searches is n log n plus r log n. So the bottom line is that the sweep line algorithm takes this rectangle intersection problem and reduces it to 1D interval search, and we have an efficient algorithm for that problem, and that enables us to solve the problem in linear arithmetic time instead of quadratic time, and that definitely enabled new progress in technology, and it's a fine example of the importance of algorithmic technology. So here's our summary of applications of binary search trees for geometric problems. We started with one-dimensional range search and just used a regular binary search tree to compute ranks to get the answer. But that, as the basis, we were able to solve the two-dimensional line segment intersection search using the sweep line algorithm. Then we looked at range search and other operations using KD trees. Again, a modification of binary search trees. And then the interval search tree to solve the one-dimensional interval search problem, and then how that corresponds to the basic algorithm that you get to if you use the sweep line algorithm to solve rectangle intersections. Many of these problems are the basis for geometric processing of huge amounts of data that we see all over the web. And our basic search tree mentality and APIs and binary search tree data structure give us efficient solutions to these important practical problems. Welcome back. Today we're going to look at hashing, which is another approach to implementing symbol tables that can also be very effective in practical applications. Here's our summary where we left off with red-black BSTs, where we could get guaranteed logarithmic performance for a broad range of symbol table operations. And the question is, can we do better than that? Is logarithmic performance the best we can do? And the answer is that actually we can, but it's a different way of accessing the data and also doesn't support ordered operations. But there's plenty of applications where the extra speed for search and insert that we can get this way is worthwhile. The basic plan is to think of the symbol table as really try to reduce the problem to being like an array. And what we do is use a function known as a hash function that takes the key, that our symbol table key, and reduces it to an integer, an array index. And we use that array index to store the key and the value in an array, maybe the value in a parallel array. Now there's a lot of issues in doing this. First thing is we need to be able to compute the hash function. That is easy for some types of data, but it can get complicated for more complicated types of data. Then the other thing is that instead of doing compare tos, we're going to be doing equality tests. So we have to be sure we've got the method that we want for checking whether two keys are equal. All we're going to do is look in the table and try to see if the key that's there is equal to the key we're looking for. And then there's the problem of collision resolution, where since there are so many possible values for a typical data type, we're going to get the situation where two values hash to the same array index. And we need a collision resolution strategy to try to figure out what to do in that case. And these things are not difficult, but they're all worth articulating as separate issues that we have to deal with in order to get an effective symbol table implementation. Hashing really, at its core, is a classic space-time trade-off. If we had no limitation on space at all, then we could have a very huge array with space for every possible key and just use the key itself as an index. If our keys are 32-bit integer keys and we've got a table of size 2 to the 32nd, then we're just fine. If there were no time limitation at all, then I would just hash everything to the same place and then do sequential search. But sequential search can be slow if we have lots of keys. So what hashing is kind of in the real world, where we're trying to trade off this idea that we don't have unlimited space and we also don't have unlimited time, so we're trying to find something in between. So we'll look at hash functions, separate chaining, and then two collision resolution methods called separate chaining and linear probing. Now we'll look at the implementation of hash functions. So idealistically, what we'd like is to be able to take any key and uniformly scramble it to produce a table index. We have two requirements. One is that we have to be able to compute the thing efficiently in a reasonable amount of time. And the other is that it should be the case that every table index is equally likely for each key. Now, mathematicians and computer scientists have researched this problem in a lot of detail, and there's quite a bit known about it. But in practice, this is something that still we have to worry about somewhat. So for example, let's suppose that our keys are phone numbers. Probably a bad idea to use the first 3 digits of the phone number as a hash function because so many phone numbers will have the same area code. And it's not equally likely that each phone number has the same first 3 digits. You have a better chance using the last 3 digits, but actually, in most cases, want to find a way to use all the data. Another example is Social Security numbers. Again, it's not too good to use the first 3 digits because they're associated with some geographic region, and it's better to try to use the last 3 digits. And the real practical challenge with hashing is that, with developing a hash function, is that every type of key needs a hash function, and you need a different approach for every key type. Now, for standard keys like integers and strings and doubles and so forth, we can count on the designers and implementers of Java to implement good hash functions. But if we're going to be implementing a symbol with our own types of data, we're going to have to worry about these things in order to get a hash function that's effective, that leads to an effective symbol table implementation. So hashing is widely used for systems programming and applications, so some conventions for hashing are built into Java. In particular, all Java classes inherit a method called hash code, which returns a 32-bit int value. And it's a requirement that if x and y are equal, then their hash code should be equal. So that's something that is a convention that's built into Java, and that enables the hash code to be used for hashing. Also, of course, if they're not equal, then you'd like it to be that their hash codes are not equal, but you can't always get that. Now, the default implementation for hashing is the memory address of the object. For hashing an object is the memory address of an object. So that kind of meets these 2 requirements for Java. The one that it doesn't maybe meet is the idea that every table position should be equally likely. So usually we'll do some more work to try to make that one happen. As far as the algorithms go, as far as the rules go, you could always return 17. That's legal. It doesn't have this highly desirable attribute, but everything would compile. So you have to be a little careful that somebody isn't in there doing that. So Java has customized implementations for the standard data types that people would use for symbol table keys, and that's the sweet spot for hashing, where some expert has done implementation of the hash code, and also your application does not need ordering. But for user-defined types, you're on your own, and we'll talk a little bit about how to implement hash codes. So here's the Java library implementations for a few standard types, and they are what they are, and what we'll do is with knowledge that that's what the hash code is, we'll do some extra work to try to get this extra property that every table position should seem to be equally likely. So if it's an integer, the hash code's supposed to be 32 bits, the integer is supposed to be 32 bits, so they just return the value. If it's a Boolean, they pick out a couple particular values that they return. Hashing Boolean types, there's only 2 different values, so well, it's hard to think about what you really might want there. For double value, this is the code. They convert to 64-bit and XOR the most significant 32 bits with the least significant 32 bits. This illustrates something that you want to do if you have a lot of bits. You want to try to involve all the bits somehow in the hash function. And for strings, it kind of treats the string as a huge number, and then really computes the value of that number, mod 32. It uses an arithmetic, a way of evaluating a polynomial or a number, so-called Horner's method, where for each digit you just multiply. So it treats it as a base 31 number, and to compute that whole number, you multiply 31 times what you have so far and add the next digit. And that's called Horner's rule, and if you're familiar with it, fine. If you're not, you can look at this little example and decide what it is. And again, it involves all the characters of the string in computing the hash function. And actually, since strings are immutable, what Java does is keep the hash value in an instance variable, so it only gets computed once. And that is going to be very effective for performance in lots of applications. So once it computes the hash code, it stores it as an instance variable, and the next time you ask for the hash code of that string, it'll just provide it. And that works because strings are immutable. How about implementing a hash code for our own type of data? And so we might have our transaction type might have a couple of instance variables, a string, a date, and a double. And we need to compute a hash code, so return a 32-bit value. And again, we want to try to make use of all the pieces of data that we have, and we also want to make use of the hash code implementations for the types of data that we're using. So one thing to do is start out with some small prime number, and this kind of mimics Horner's method to just add in more data as we get it. So we pick some other small prime number, and for each field we multiply by 31 and then add the hash code for that field. If it's a reference type, we just use the hash code. So who is a string, so string has a hash code method, so we add that in. And dates, when's a date, so we add that hash code, multiply by 31 and add that hash code in. Trying to take all the bits and scramble all the bits and use them. And for primitive types, take the wrapper type and use the hash code. So that's a simple example of implementing a hash code for our own type of data that might include several different types of instance variables. So that's the standard recipe. Use the 31x plus y rule to combine all the fields. If it's a primitive type, use the wrapper hash code. If the field is null, return 0. If it's a reference type, use that hash code and apply it recursively. And if you have an array, you have to apply it to each entry. Or actually, Java implements that in the its arrays library. So this recipe works pretty well in practice, and it's used in several in Java's libraries. Now, in theory, it's possible to do something that has the property that that all positions are equally likely. It's called universal hash functions. These things exist, but they're not so widely applied in practice. So the basic rule is if you're computing your own, try to use the whole key, but consult an expert if you're seeing some performance problems or you really want to be certain in some performance critical situation. Now, what we get back from a hash code is a int value that's between -2 to the 31st and 2 to the 31st minus 1. Now, what we need is, if we have a table of size m, an array of size m that we're going to use to store the keys, we need an int value between 0 and m minus 1. The value of m is maybe a power of 2, or sometimes we pick a prime because of the way that we normally would get the big hash code value down to be a number between 0 and m minus 1 is to just do mod m. And if m is a prime, then from math, modular arithmetic, we know that we're using all the bits in the number in that point too. Since the hash code can be negative, this doesn't quite work the way this arithmetic's implemented in Java, because it's 1 in a billion times. You really have to take the absolute value. You have to take the absolute value because otherwise it'd be negative, and you can't have a negative. You want it to be between 0 and n-1. But even if you take the absolute value, there's going to have -2 to the 31st is possible. So you have to just take the 31 bits. You get the hash code out, make it positive, and then mod m is the way to go. The math doesn't quite work out right. So anyway, that code down at the bottom is, you can use that as a template for what you might want to do. And that's what we do in order to get the hash code to be a number between 0 and n-1. And if m is prime, it gives us some comfort that we have some possibility of each table position appearing with equal likelihood. So that's our assumption, that each key is equally likely to hash to an integer between 0 and n-1. And this assumption, again, it's with work, it's possible to come close to this. Lots of researchers have done good work to show this. And so we'll assume that as a starting point. And that allows us to model the situation with the so-called bins and balls model that directly relates the study of hash functions to classical probability theory. So we've got m bins, that's our corresponds to our hash table, and we got m balls, and we have some number of balls, however many keys we have, and we throw them uniformly at random into m bins. And these things are studied in classical combinatoric analysis. For example, there's the birthday problem, which how many balls do you throw before you find 2 hitting the same bin? When do you get the first collision? And the answer to that is it's about square root of pi m over 2. When does all the bins fill up? Well, that's called the coupon collector problem. After about m natural log m tosses, every bin has at least 1 ball. And those are just examples of classic results from combinatorial analysis that help us understand what happens when we do this, which is what we're doing with hashing. And we'll look at more advanced versions of these problems when we want to study hashing. In particular, it's known that after you've thrown m balls into the m bins, then the most loaded bin has about log m over log m balls. So that's going to help us get a handle on the performance of hashing algorithms when we get to the implementations. So this is just an example showing all the words in A Tale of Two Cities using the modular hashing function for strings, like the one that Java uses, and they're pretty uniformly distributed. That's the summary for hash functions. So let's just look at a little bit of the context of hashing in practical applications. As I mentioned, it's very widely used. So here's an example right from Java. The first implementation of Java 1.1, the designers found that the cost of computing the hash function for strings seemed to be excessive, particularly for long strings. And that was one of the main uses of hashing, was just to be able to do searching with string keys. And so what they decided in the first implementation was, let's just look at every 8th or 9th character. In that way, we don't have to spend a lot of time computing the hash function. So they had a hash function pretty much like the one that we use, except they'd compute a skip that would mean that they'd only look at about every 8th key, and they wouldn't have to do quite so much work performing the hash function. And that's definitely one thing to consider when using hashing, is that the cost of computing the hash function for a complicated key might exceed the cost of searching in using a simpler structure like a binary search tree. And anyway, for Java 1.1, what happened was that there was a huge potential for really bad collision patterns on typical data. So here's an example of typical data, which is a URL. All of these keys, which are totally different, would wind up having the same collision. And so client programs and system programs in the Java system were having terrible performance on their symbol table because of this shortcut in hashing. So this well illustrates that you need to use all of the data in the hash function. And sometimes when you do a closer analysis, the cost of the computing the hash function can mean that something like red-black trees will even outperform hashing even for just search and insert. So there's another thing about the uniform hashing assumption is that it is an assumption, and if you're writing code where we have to have guaranteed performance, like when your aircraft is landing or you're controlling a nuclear reactor or somebody's pacemaker, if that assumption doesn't hold and you get bad performance, you're going to have disastrous consequences. So that's another reason to think about maybe paying a little extra and using the guarantee that you get with red-black search trees instead of hashing. And there's another surprising situation that happens in today's world. For example, Java publishes its hash functions. And so if you're trying to provide a service over the web, an adversary can learn your hash function and just send you data that causes a huge performance problem by just making all that data hashed to one particular item. And that's definitely something to worry about. And in the real world, you can nowadays find on the web particular sequences of keys that will cause particular services to crash. And again, that's a little harder to do with something like a red-black tree where we have performance guarantees. When you make an assumption, you better be sure, and you're depending on that assumption, you better be sure that it holds somehow. And this is different than, for example, for quicksort, when our assumption was we're going to create randomness and we're going to depend on that randomness. In this case, we're kind of hoping for randomness, and maybe that doesn't really always hold. So that's certainly something to be aware of when using hashing in practice. So here's just a simple example on hashing in Java. So what we can do is it's pretty easy to find a family of strings that have the same hash code. For example, with just a little fooling around, or nowadays you can just look it up on the web, you can see that these two-character keys both have the same hash code. And you just do the math, and that base 31 hash code will tell you that answer. Well, what that means is that actually, just like working in binary, you can combine those things in all possible ways, and you can get 2 to the n strings for any n of length 2n that all hash to the same value. And somebody's implemented a service in Java that uses a symbol table that takes string keys. You can cause that to crash in this way. A little bit scary for some systems designers, at least reason for pause in using hashing. Now, hashing also has an extremely important application in today's internet commerce. So it's the concept of so-called one-way hash functions. Which means that we use it for secure, to try to have some secure fingerprints for use on the web. And there's been a lot of research done to develop functions that take keys as input and then produce values that look random in such a way that it's hard for someone else to find another key that collides with that. This technology is useful for storing passwords and digital fingerprints and things, but it's too expensive for use in a symbol table. So the bottom line is separate chaining versus linear probing as collision resolution methods. There's a number of considerations to take into account. Separate chaining is really easy to implement, both insert and delete. If performance degrades, it does so gracefully. And the clustering is maybe less of a problem if you have a bad hash function. Linear probing tends to make better use of space, and also it'll perform better for huge tables where caching is involved. And the classic algorithm or computer science problems for people to think about is what do we do to delete in these two situations, and exactly how do we resize? And those are all at the level of exercises in the context of the kinds of algorithms that we've seen. And as I mentioned, there's been many improved versions of hashing that have been studied. I mentioned the two-probe or double hashing version. Another way to use two hash functions is just to hash to two positions and put the key in the shorter of the two chains. In that case, then the expected length of the longest chain will be log n, which is quite an improvement. You get constant time expected and log n worst case. Double hashing is the variant of linear probing where you just skip a variable amount, not one each time, and that pretty much wipes out clustering, but it is more difficult to implement delete for that one. In a new method called, a relatively new method called cuckoo hashing, is another variant of linear probing where we hash a key to two positions and insert the key in either one. If occupied, you reinsert the displaced key into its alternative. It was in one, each one can go to two. And that one actually gives constant worst case time for search. That's another variation on the theme. And all of these things allow us to make better use of the memory, allow the table to become nearly full. Would have been very exciting to the researchers in the 1950s who cared so much about memory. Nowadays, a little extra memory is not something that people care about so much, and most people just go with the easy algorithm, except for really performance-critical applications. What about hash tables versus balanced search trees? Well, hash tables are really simple to code, usually, if you don't have to do the hash function. If you don't have order in the keys at all, then you need the compare to implement balanced search tree. So you have to use hashing if you don't have comparison. And it'll probably be faster for simple keys to use hashing. It's a few arithmetic operations to do the hash versus log n compares for the balanced tree. And there's some better system support in Java for strings. That cache hash code means that you don't even have to compute the hash if your symbol table for strings is in an inner loop. On the other hand, balanced search trees have a much stronger performance guarantee. You don't have to assume anything. It's going to be less than log n compares, and it's got support for all those ordered ST operations, and compare to is a pretty easy and natural function to implement. So it's more flexible and more broadly useful. And actually the Java system and other systems include both, so that programmers can make use of either one in different situations. That's our context for hashing algorithms. Another popular collision resolution method is known as linear probing, and there's many different versions of hashing that are based on this idea. With linear probing, it's called open addressing, and it's also around the same time in the 50s. The idea is to just use an array instead of using space for the links in a linked list. Use that same space and just allocate an array. In this case, the size of the array is going to have to be bigger than the number of keys that we expect. And we use empty slots in the array to essentially terminate the length of the list that we have to search through when we're doing a insertion. So let's look at a demo of how it looks. So to hash, again, we do the same thing. We just map the key to an index. But in linear probing, to insert, what we do is we put it in position I if that's free. If not, we just look at I plus 1 and I plus 2 and wrap around to the beginning if we reach the end. And that's also very simple to implement, and it works well as long as the size of the array is significantly bigger than the number of keys. Let's look at a demo. So start with an empty table, insert S. Its hash value is 6. 6 is empty, so we put it there. Now we look at E. The hash of E is 10. We look at 10. It's empty, so we put E there. So at the beginning, we're going to be fine. A is 4. Empty, put it there. R is 14. Empty, put it there. So we're just essentially using the hash function as an array index. C is 5, that's empty, and we put it there. So H now, the hash value of H is 4. So now we look at 4, and that's occupied, so we can't put the H there. And then linear probing says, just look at the next position, look at 5. That's still not empty, so we look at 6. We keep going till we find an empty place, and then we put H there. Now when we search, we're going to have to do the same thing. We're going to have to look at all those positions to look at H. The group of 4 contiguous keys in a table space there is called a cluster, and clearly we want to keep those clusters small. And we do that by just not putting too many keys into the table. So X hashes to 15, that's empty, so we put it there. M hashes to 1, that's empty, and we put it there. P hashes to 14, 14's occupied, 15's also occupied. Now we run off the end of the table and look at 0, and that's empty, so we put it there. L hashes to 6. 6 is occupied, we look at 7, 7's occupied, we look at 8, and we put it there. And so that's an example of inserting keys into a hash table. And now for search, we just do the same thing. We use the hash function to search for E. E's hash value is 10, so we look in 10, and there it is. So that's a search hit. If we're going to search for, say, L, L's hash value is 6, so it's not there. So in order to look at every place in the table where L could be, we have to keep looking until we find an empty table position, or we find L itself. So now we look at 7, L's not there. We look at 8, L is there. That's a search hit. If we have a value that's not in the table, like K, well, we'll hash, and is it in position 5? No. 6, no. 7, no. 8, no. And we find an empty position. At that point, we can conclude that K is not in the table, because if K were in the table, it would be somewhere between its hash point 5 and that empty position 9. That's a search miss, and we return null. So that's a short demo of linear probing hashing. So here's a summary of linear probing hashing. To get started, we map a key to an integer between 0 and m-1, where m is the size of our array where we're storing the keys. To insert, we put the key value pair, use parallel arrays, a key in one array and a value in an array with the same index. And we put the entry at table index A if it's free. If not, you try I plus 1, I plus 2 until getting to an empty position. And for search, you do the same thing. You hash to the table position, and you look there and to the right to find the key, and you stop when you find an empty table position. Find the key or find an empty table position. Now, it's essential that the array size is greater than the number of key value pairs in. And for linear probing hashing, really the implementation needs to include array resizing whenever the hash table gets too full. Usually, as we'll see, it's a good idea to make sure that it stays at least half empty. Here's the implementation, and it's quite straightforward given the demo that we talked about. Use the same hash function. We use parallel arrays for the value in the keys, and we have to use ugly cast because we can't have arrays of generics. Then let's do the search. So we just have a for loop starting at hash of key and going until we get to a position that's null. As long as it's not null, we stay in the loop. And increment I mod m, so that's when I gets to the end. It's at position m minus 1, then it goes, next increment goes back to 0 to the left end of the table. And we just test for all the non-null keys. If it's equal, if it is, go ahead and return the associated value. And if you get to an empty position, then return null. And the implementation of put is similar. Find a position if it's that's equal, and then reset the key and the value. If the key's there, it just resets the value. If the key's not there, it puts a new entry in. So again, that's fairly little code to implement a fast symbol table and insert, search and insert, but it's only going to be fast if the table size is set appropriately. In ancient times, memory was at quite a premium, and so people were very concerned in making sure that the hash table never got too empty. Remember, in the first computers, each bit was a physical thing, a magnetic core that somebody had to string a wire through. So the bits were really expensive, and people wanted to make sure that they were making best use of the memory. And just leaving empty positions around in a hash table or using links in a linked list did not seem like an appropriate use of space. And so there was quite a bit of effort devoted to figuring out how full we could get the hash table in linear probing and how close it could get to being full without sacrificing performance. And one way to think about what goes on is to just watch what happens when a hash table fills up. So here we're just, as it goes up, we're showing each key getting inserted and the number of probes of the table that are needed for the insertion. So J hashed to the same position at A, and it had to look for a while. And one thing to notice as the table gets full is that, first of all, you have these clusters or these chains building. And so what's clear about that is that it means that the new hash is likely to hash into a big cluster. And not only that, once you have a big cluster and you hash into the middle of it, you've got a good chance that that cluster is going to get longer, or worse, that it's even going to merge with another big cluster. And so that's the situation as the table fills up. You get long clusters, and they're likely to get longer. And the math bears that out. Now, this was studied in detail by Don Knuth in the 1960s. And actually, this problem, Knuth says, was really the origin of analysis of algorithms. Mathematicians were trying hard to understand this problem and were ready to give up. And he realized that you could use classical balls and bins type probabilistic analysis. Not an easy analysis, but we actually could make precise, accurate statements about the performance of this algorithm. And those statements could be borne out in practice because the hash functions approximate random, the math assumes random, and the formulas predict what actually happened in practice. And the way Knuth formulated the problem is a so-called parking problem. So what's happened is you're at a one-way street and you're looking for a parking place. And it's the idea is you start looking for a parking place at a particular time, say, okay, now I need a parking place. And what you're doing is linear probing hashing. If the current space is taken, you try the next space and the one after and so forth. And the question is, if every car starts looking for a place at a random time, that models the hash function, then how far do they have to go to look for a place? That's Knuth's parking problem. And he was able to show, and we'll talk just a little bit about this, that if there's only half of the parking spaces are occupied, then on average, half the people find it after one place, and the other half have to look one extra. So that's the kind of performance that we want. But as it gets full, the displacement gets up to square root of pi m over 8, which is obviously much higher than we want. We don't want our searches to take that long. In that, actually, the analysis is an amazing function that goes back to the famous Ramanujan and other classical results from combinatorial analysis. What Knuth's theorem says is that under the uniform hashing assumption, the number of probes in a linear hash table of size m that is alpha percent full, so the number of keys is a fraction of m, is for a search miss, half 1 plus 1 over alpha, and a search miss, 1 plus 1 over 1 minus alpha squared. 1 minus alpha for the hit, 1 minus alpha squared for the insert. Now, as alpha gets close to 1, you can see these things are going to grow, and particularly the search miss is going to grow quite a bit. If it's 9/10 full, 1 over 1 minus alpha squared is 1 over 100. So it means there's going to be 50 probes for a search miss if it's 9/10 full. And that's independent of n and m. Whereas if it's half full, then we get the nice numbers of only 3 halves for a hit and only 5 halves for a miss. And again, these formulas are nice approximate formulas, but Knuth, once he figured this out in 1963, tells the story as at that time he decided to write his famous series of books on algorithms. And now there's 4 volumes out and more planned, and this is where all computer scientists go for detailed information on the performance of algorithms. So in summary, you can't have m too large. What we want to use nowadays is array resizing to make sure that the array is always about half full. And if we can keep the array about half full, then we get constant time performance for search hit and search miss. And linear probing is very attractive in this case. There's other things that we can do algorithmically to bring down the search time a little bit, like using another hash function rather than looking at the next entry, use another hash function to determine the stride that we're going to use, and that brings it down somewhat and allows us to keep the tables more full. But the bottom line is that now we have 2 methods that, under the uniform hashing assumption, can give us constant time search hit, insert, and delete. For symbol table implementations where we don't need ordering and we've got a reasonable hash function. So that's a summary of linear probing, our second hash collision avoidance strategy. Next, we'll look at separate chaining, a collision resolution strategy that makes use of elementary linked lists. So what are we supposed to do when 2 different keys hash to the same index? The birthday problem tells us that we're going to have collisions. You need a quadratic amount of memory to avoid collisions. And the load balancing and coupon collector analysis tell us that the collisions are going to be evenly distributed among the table, around the table. So what we want to do is have an easy way to deal with collisions. And so the first way we'll look at is called separate chaining, and it's a very old idea going back to 1953. And the idea is just build a linked list for each of the table positions. So we'll have a table that's smaller than the number of keys that we have. The hash function will map each key to some integer. So in this case, we have a table of size 5. So the hash function will map any key. In this case, we'll use single letter keys. It'll map any key to an integer between 0 and 4. And then to do an insertion, we'll just keep a linked list at the table position corresponding to the hash value. So S hashes to position 2, it'll be on the linked list that first link is at position 2. And then E goes to 0 and A goes to 0. And for search, we're going to have to go to, if we're going to look at is C in this table, say, we're going to find the hash value for C, and we'll look down the list to see if we can find C. So we have to look through the whole list for search, but you only have to look through one list out of all the lists. Essentially, if you have M entries in the hash table and n keys, the length of the list you're going to have to look at is about n over m because they're evenly distributed. So that's a straightforward and simple scheme for implementing symbol tables with hashing. Now, we could use a iterable bag or some data structure like that and hide the linked list structure underneath, and that's a perfectly fine way to proceed in modern programming. This implementation directly implements the linked lists. Now, for a practical situation, we pick some value of m. You could make it so that the hash table itself grows once it gets really huge, and such hybrid methods are easy to implement, so we won't talk too much about that. We need to, just in terms of implementation details, our keys and values have to be objects because we can't have an array of generics. Since we're making an array of nodes, and node would have generics if we're used to key and value, so we have to make them objects, and then when we get things off, we're going to have to cast. This is the get procedure. So to look for a key in the hash table, we compute a hash value, and our hash function is pull out the system hash code, make it positive by ANDing off the sign bit, and then mod with m to get a number between 0 and m minus 1. So we pick that number I, and then we just go to that list, and this is the standard code for traversing a linked list. Start at the first node, as long as it's not null, go x equals x dot next. And if you find a key that's equal to the key you're looking for, return the value, and we have to cast it to value because of the generic array creation problem in Java. Otherwise, you return null. So that's not much code, and it's trivial code at that for doing an efficient symbol table search using hashing. And insertion is not much more difficult. If you do the same thing, and if you find a node with key equal to the key on the linked list, you reset the value and return. Otherwise, you make a new node and put it at the beginning of the linked list with this standard code. Replace st of I with a new node that links to the old st of I. So again, very little code to implement search and insert using hashing, and that's why it's so popular. And what about the analysis? Again, the standard probabilistic analysis of the balls and bins problem tells us a lot of information of what goes on. And again, if the uniform hashing assumption holds, the probability that the number of keys in a list is within a constant factor of n over m is extremely close to 1. So it means that we've divided the search cost, which would be n if we have a sequential search, by a factor of m. And in many applications, even setting m equals to 100 or 1,000 is going to be very effective, and that's why so many systems programmers use that. So number of probes for search and insert is proportional to n over m. Now, typically what a programmer would do is try to figure on making m about equal to the number of keys divided by 5, say. So if you can't make M too large, you have too much space, and you'll have empty chains or short chains. And if you make M too small, then they're too long. You have to search through them all. So let's say N over 5, and then you get constant time searches and not much extra space. You have extra space for the links to implement the linked list, but the rest of the table is not much extra space. And those are typical parameters. If you want a full service symbol table, which is going to grow from small to huge and then back down to small again, then you'd want to use array resizing to make sure that M is always within a constant factor of N, but we'll leave that detail out for now. So that brings us to this summary. Where red, black trees, we were happy with log base 2 of n for search and insert. With separate chaining, you can really get it down to a constant number of operations for search and insert. So hashing's going to be preferred for short keys where the hash function's easy to compute and where we don't need ordered iteration or any of the ordered symbol table operations because it has really fast access to the symbol table. That's our first collision resolution method, hashing with separate chaining. Now let's look at a dictionary client, another very useful and common application of symbol tables. So in this case, we're going to write a client called lookup CSV that is going to take 3 arguments. The first will be a file name, a so-called comma-separated value file, and the next 2 arguments are integers, which will tell us what to treat as keys and values in the file. In this example, our CSV file relates URLs to IP addresses. So each line has a URL and an IP address, and they're separated by commas. And in general, a CSV file might have many fields separated by commas. So we number them 0, 1, and so forth, starting from the left. So what we are going to do with this client is specify with integers which field is the key and which is the value. So if we call this client with the second argument 0 and third argument 1, that means we want to use the URL, field 0 in the CSV file, as the key, and we want to use the IP address, that's field 1 in the CSV, as the value. We want to associate keys with values. So the client will build a symbol table that makes those associations for every line in the file, and this could be a huge file. And then if we want to look up the IP address associated with a given URL, we can just type in URLs and the client will return the IP address. It'll do the lookup. So adobe.com has got this IP address as shown at this line here in the table and so forth. Princeton.edu has this, and ebay.edu is not in the file. Now, on the other hand, we could, from this same file, we could build a symbol table where we treat the IP address as the key and the URL as the value. So in that case, it'll build a symbol table with IP addresses as keys, and we can type in an IP address and get the associated URL. So with one client, we can handle lookups of all kinds in CSV files. For example, here's another CSV file that from biology that deals with amino acids and codons and names. So in this case, the first field is 3 letters from a DNA sequence, which represents a codon, and certain codons have the names. That's the amino acid. So TCC is called serine and so forth. And that's an association that's well known to biologists. And then you can use this lookup CSV client to quickly get the name associated with any given codon. And that's just another simple example. This is a very general tool. Any CSV file, you can pick any field as the key and any other field as the value. So here's still another example where we might use for a class list, which has the person's year of graduation, last name, first name, precept name, and login name. And so in the first call over here, we might use the login name as the key and the first name as the value. So we type in somebody's login name, we get their first name. And again, with the same client, log in as key and get the section as a value. So all kinds of information processing that we might need to do for large amounts of data represented in comma-separated value files. This one client, which is based on a symbol table, will provide useful functionality. And here's the implementation. There's very little to it, given the symbol table API that we've articulated and the implementations that we have. So what do we do to get lookup CSV implemented? Well, first thing is to set up the input stream from the first argument, so that's our input file, and then get the numbers of the fields, so the key and the value, and now build a symbol table that associates strings with strings. Then there's a while loop where we just read a new line, read line, and then split according to comma into tokens in an array. And then the index in the array is going to be the fields that we're going to use. So the key is the string in the key field entry of the array, and the value is the string in the val field entry in the array, and we simply put that in the symbol table. So this while loop just builds the symbol table from the file. Then from standard input, we take queries, just read a string, check if the symbol table contains the string. If it doesn't, print not found, and if it does, print the value associated with the key. So a very small amount of code based on our symbol table implementation that gives us the dictionary functionality. Here's another simple client program for symbol tables related to indexing. Again, another common function that's easily handled by symbol tables. There's all kinds of cases where we just have a lot of information, maybe on our PC or all over the web, and we want to create an index that allows us to specify a search key and get all the associated information. And you've used programs like this on your computer in many instances, most likely. So more generally, here's the goal. So we're going to have a list of files that are specified, and then and maybe it's all files on the computer, or maybe it's specified in some other way. And what we want to do is create an index so that we can efficiently find all the files that contain a given query string. So in this small example, so our client is going to be called file index. And in this small example, say we're going to have 5 text files. And these are just pieces of literature. And so what we want to do is build an index from that set of text files. And then given a key, a string key, we want it to print out the files that might contain that key. So for example, the word freedom appears in the Magna Carta and in Moby Dick and in Tale of Two Cities, all 3 of them, but not in Tom Sawyer and not in Aesop's Fables. The word whale appears only in Moby Dick. The word lamb appears both in Tom Sawyer and Aesop's Fables, and so forth. So we're looking for a piece of information somewhere on a computer, and it'll give us the names of the files that contain that information. So with a more complex user interface, this is very much what the spotlight or find function on your computer is doing. And a programmer might use the same program to find places where certain programming terms are used in a bunch of programs. So normally we have a bunch of .java files when we're working on an application. Like these are all the ones associated with this lecture. So we might build an index from that set of files, and then we might wonder, well, where do we use the import statement? So we just search for import, and it'll tell us, look in those 3 files. Or did we use comparators anywhere here? And this index will tell us no. So again, a very general capability that's got lots and lots of applications and easy to implement with our symbol table API. And the idea is that what we're going to do is associate keys with values. Well, the key is the string we type. What's the value? Well, what we're going to use for value is a set of files, the files that contain the query string. So just given that high-level description, then the implementation is pretty direct. Here's the implementation of file index using our symbol table implementation. So now we're going to build a symbol table that associates string keys with sets of files. So this creates a new symbol table associating string keys with sets of files. So first thing we do as before is build the index. So we're going to take, this time we're going to take the list of file names from the command line. And for each file, we're going to create an input stream. We're going to read every word in the file. If the symbol table does not contain the word, we'll create a new set for that word and put that into the symbol table. And then we simply get the set associated with the key and add the new word to that set, the new file name to that set. So this one, for each word in the file, it'll add that file name to the corresponding set for that word. That's building a symbol table associating keys with sets of files. And then processing queries is the same as before. As long as standard in is not empty, we take a query and then simply print out the set of strings associated with that word, which is a list of file names. So again, our symbol table API gives a very easy way to implement this file indexing function, which is very widely useful. And similarly, maybe we want to build a book index, maybe for a real book or maybe for an ebook. Or more generally, people want to often pre-process text, maybe a huge amount of text, to support so-called concordance queries. So what you want to do is, given a word, you want to find all occurrences of that word along with the immediate context. And context just means a few words before and a few words after. So for example, in Tale of Two Cities, the word cities actually only appears in this one place, and this is the context that it appears, with the four words tongues of the two before and that were blended in after. The word majesty appears in three places, and there's the context. And while this is a very special case of what you're very familiar with in web searches, you type in a word and then you get places where that word appears in context. Again, our symbol table API provides for an easy way to implement this. This is a concordance client that does the job. Now what we want to do is read text, and we want to build an index for each word. So this is a Java construct for reading all the strings on an input stream, on standard input, and splitting them by blank space and putting them into array. So now all the words are in an array on standard input. And then we're going to create a new symbol table that associates strings with sets of integers. And again, the string is the key, and the sets of integers are going to be the places in the array where the given word appears. So we go through all the words, pick out our key S, and again, if it's not there yet, we create a new set associated with that S. And then afterwards, we go ahead and get that set and put the new index on that set. And then that allows us to process queries where we take a query and then get the set of indices associated with that query, and then we've left out the code where you print out the 9 words that you want, the 4 to the left and the 4 to the right. Again, quite useful and familiar functionality and very easy to implement with our symbol table client. As a final example of a symbol table client, we'll take a look at a mathematical application where we want to implement sparse vectors and matrices. So this is standard matrix vector multiplication that you learn in math, where we have a square matrix and a column vector, and we want to do a dot product of first row with the column vector to get the first entry in the result. So in this case, they're all 0 except for 0.04 times 0.9, which is 0.36. And then similarly, dot product of this with that column is 0.297, and so forth. So standard implementation of this is quite easy. We have a two-dimensional matrix, one-dimensional column vector for the multiplicand and the result. And then they get initialized in some way, but the main computation is a pair of nested for loops. For each row in the matrix, we have to go through each entry in the column vector and compute a running sum of, for that row in the matrix, the corresponding entry with the entry in the column, and keep the running sum, and then that's the result that we put in the result column vector for every value of I. And the key thing about this standard implementation, that it's two nested for loops that each run up to n, so that's n squared, or quadratic running time. And that's fine in typical applications when the matrix is small, or when there's lots of entries in the matrix. But the fact is that in many practical applications, the matrices are what's called sparse. Most of the entries are 0. And so symbol tables provide us with a way to provide a more efficient implementation of this process when we have lots of 0 entries. So in a typical thing, say maybe the matrix dimension would be 10,000, and maybe there'd only be 10 non-zero entries per row. Or even nowadays, you might have matrices that are even bigger, 10,000 by 10,000. If it was full, that'd be 100 million entries. So that's definitely going to be costly if you're doing this operation a lot. And the idea is to cut down on that cost by taking advantage of the idea that there's a lot of zeros. So let's start by just looking at vectors. The standard representation that we use for vector is to simply use a one-dimensional array. We have constant time access to every element, but the space is proportional to n. So even if there's a lot of zeros, we still have to take the space to store them all. Instead, we're going to use a symbol table representation where our key is the index and the value is the entry, and we just use that for every non-zero entry in the vector. So this has got the same amount of information. It says that index 1 has got 0.36, index 5 also has 0.36, index 14 has 0.18, and so forth. But the space is proportional, instead of to n, it's just proportional to the number of non-zero entries, which again in typical applications may be way, way less. And so now just we know we have a symbol table implementation that has efficient iterator, and also access is not bad. It's just that we're able to do it with way less space. So here's what the implementation of a sparse vector might look like. First thing is the representation is going to be a symbol table, and in this case we might as well use a hash table because the order in which we process things is not important. We just want to get at all the non-zero entries. The constructor is going to create in this symbol table, just a new symbol table that associates integer indices with double values. So the put, which is to store a value associated with an index I, is just put into that hash table, associate key I with value X, associate an integer with a double. And get, returns 0 if the index key is not in the symbol table. We didn't, as the whole point was, we don't represent zeros. Otherwise, it returns the value associated with the index. And the iterable just returns all the key to iterate. And the most important thing is that if we want to do a dot product with a vector, say, then the time that it takes is only proportional to the number of non-zero keys. The 0 keys are going to be 0 in the dot product, so all we're going to do is take the ith entry of the vector and multiply it by whatever value we get for the non-zero entries. So it's a dot product that takes time proportional to the number of non-zero entries in the vector. And that's going to be important in the use of a matrix. So instead of using the standard matrix representation where every row of a matrix is an array, that's what a two-dimensional array is, and the space is proportional to n squared, now we're going to use a sparse matrix representation where each row of the matrix is a sparse vector. We can iterate through the elements in constant time, and with the hash table even get at them in near constant time. And then constant time in the average. But the space is only proportional to the number of non-zero elements, plus n for the extra symbol table overhead. So those are independent symbol table objects, but they allow us to have a much more efficient matrix multiplication method. So now, if we have a sparse matrix times a vector, our running time is going to be constant for each row, or proportional to the number of non-zero entries for each row, which means that the running time is going to be linear for a sparse matrix just by the use of a symbol table. And this clearly can make the difference between being able to address a huge problem. If we have a 10,000 by 10,000 matrix, we can get it done nearly instantly linear time versus 10,000 squared. If we don't run out of space, we might run out of time. But with the symbol table implementation, we can efficiently process huge sparse matrices. Welcome back. Today we're going to look at some symbol table applications to give you some idea of how symbol tables might be used by client programs for practical problems. First one we'll look at seems even simpler than regular symbol tables, and that's about sets. So a mathematical set is just a collection of distinct keys. And so there's plenty of applications where we want to just be able to implement this really simple API. We want to be able to create an empty set. We want methods to add a key to the set and to check whether a given key is in the set or not, to remove a key, and maybe return the number of keys in the set, and also have an iterator to iterate through keys in the set. This is simpler than symbol tables because it's got no associated value. That's a very simple API, but of course we want to be able to do these operations efficiently. How would we go ahead and implement that? Well, if you think about it for just a minute, you see that what you need to do is just remove all references to value from any of the symbol table implementations that we look at. The implementation is easy. Take one of our symbol table implementations and get rid of the code that refers to values. Okay, so let's look at a couple of applications where this set API might be useful in client programs. One thing that is very common is the idea of an exception filter. So the way we'll set that up is to think about having a list of files, a list of words in a file that are exceptional in some way. In this case, we'll have the file list.txt that has these 4 words in it: was, it, the, and of. So there's 2 complementary ways to look at this. One is so-called whitelisting, where we want to take the words in that file, and then we have some other much bigger file, And what we want to do is print out all the occurrences of our exceptional words in our given file. Those are the ones that we care about, that we want to get through. So in this case, tiny tail.txt, the first couple of words from Tale of Two Cities, and these words appear often. It was the of, it was the of. Another complementary approach is to think of these words as words that we don't want to ever see. They're blacklists, and we want to take them out of our source file. So a blacklist client would print out all the words in our source file, tinytail.txt, except was it, the, and of. In this case, best times, worst times, and so forth. So that's an exception filter, and that's useful in lots of applications, such as the ones listed here. For example, you might have a spell checker where you want to identify misspelled words. So then your key would be a word or string, and in your exceptional list would be words that are in the dictionary. And you'd want to print out all the words that are not in the dictionary. That's an example of an exception filter. Or in a browser, you might want to mark your visited pages or block sites and so forth. Or like the one at the bottom, credit cards. Maybe you run a credit card company and you want to check for stolen cards. Then your keys would be numbers, and in your list might be kind of short, which would be the stolen cards that you know about, and you'd want to run a whitelist filter for those cards and print out in your long list of transactions whichever transactions have that stolen cards. So that's just a couple of examples of exception filters. What's the implementation of an exception filter? Here's a simple one using the set API that we just articulated. So we start by creating an empty set of strings. And again, since we don't have associated values, we just have the one generic for strings. And then create a new input stream from the first argument, so that's the name of the file that contains the exceptional words. And so this just reads those strings while the input string is not empty, and then adds them to the set. So that now we have our set of exceptional words, and now from standard input we read words. As long as our set contains the word, we print it out. If it doesn't contain it, we don't print it out. So that's an example of a whitelist filter. And to implement blacklist, we just this call to contains, we just change that to a not. If it's not in the exceptional list, then we print it out. So that's a simple example of a filter using sets.